Hi students, welcome to our YouTube channel Knowledge Academy. The main of this lecture is discuss about the formulas which are useful for examinations of the GATE and also IS. So in this playlist we are going to discuss about the mathematics portion or mathematics formulas which are very useful for the examinations of the GATE examination and also IS examination, and also some of the state examinations also they are going to include this mathematics portion, and definitely these formulas are going to give you a quick revision in order to solve these questions in a very much short amount of time. So in this lecture we are going to discuss about the linear algebra. So linear algebra, the first thing is about the matrices. Suppose there is a matrix M, so you can see clearly there is a matrix M. So for this matrix M, you can see clearly here Aij M cross N. See Aij M cross N, it is nothing but here Aij indicates that the number of elements which are present in the matrix M, and M cross N, where M is called as the number of rows and N is called as the number of columns. So here M indicates the number of rows which are going to present in this matrix, and also N indicates the number of columns which are going to present in this matrix. Suppose you can see clearly there is another matrix M with Aij 1 cross N. So you can see clearly here M is equal to 1. See, M is equal to 1 indicates that there is only one row but there are n columns. So we can say this matrix is going to contain only one row. So therefore we can call this matrix as a row matrix. Whereas you can go for the another one. Here M is equal to Aij n cross 1. So you can see clearly here the number of rows are not equal to 1 but the number of columns are equal to 1. So you can see clearly here we can say simply this matrix is going to contain only one column, so we can call this matrix as a column matrix. So simply we can say if any matrix contains only one row, we are going to call that matrix as the row matrix, and if a matrix has one column, we are going to call that matrix as the column matrix. And now we will go for the another matrix. Suppose there is a matrix M with Aij n cross N. So you can see clearly the number of rows is equal to the number of columns. If the number of rows is equal to number of columns, we are going to call that matrix as a square matrix. If any matrix, if the number of rows is equal to number of columns, we are going to call that matrix as a square matrix. And all the elements which are going to present in the diagonal, or we can say the principal diagonal, see the number of all the elements which are going to present in this principal diagonal are called as the diagonal elements. So simply we are going to call it as the AII. It indicates that A11, A22, A33 and goes on. So all these elements which are going to present in the principal diagonal, we are going to call it as the diagonal elements. And suppose if the number of rows is not equal to number of columns, then we can't simply, we are going to call it as a rectangular matrix. If the number of, you can see here, you can see clearly, if suppose M is not equal to N, then definitely we are going to call that matrix as a scalar matrix. But suppose if the number of, suppose here the number of rows is not equal to the number of columns, then we are going to call this as matrix, we are going to call it as the scalar matrix. So this matrix we are going to call it as the scalar matrix. And now we will go for the other one, which is, so now there is another matrix M. So for this matrix M, Aij M cross N. So Aij M cross N, you can see clearly here Aij is equal to 0. Here Aij is equal to 0 for all I comma j. It indicates that if Aij is equal to 0 for all I comma j, it indicates that each and every element in that matrix is 0. If each and every element in that matrix is 0, then we are going to call that matrix as the null matrix. Or simply we can say each and every element in that matrix is 0. So therefore we are going to call this matrix as the null matrix. So if we add null matrix to any other matrix, then we are going to get that matrix itself. So therefore A plus M is equal to M plus A is equal to A, because M is a null matrix. So if you are going to add null matrix to any other non-null matrix, then definitely you are going to get the result as a non-null matrix. So therefore we can say A plus M is equal to M plus A is equal to A, because here M is a null matrix. And now we are going to go for the other one. Suppose in this one there is a matrix M. If M is equal to Aij n cross N, it indicates that, see, whatever the matrix we are going to take, and it is called as a square matrix. And if Aij is equal to 0, when I is not equal to j. It indicates that here except the principal diagonal, remaining all other, means we can say simply except the principal diagonal, remaining all elements are 0. So therefore we are going to call this matrix as the diagonal matrix. Means except principal diagonal, remaining all elements in the matrix, if they are 0, then we are going to call this matrix as a diagonal matrix. And here now, suppose there is a matrix M with Aij n cross n. So for this matrix Aij n cross n, if Aij is equal to 0 when I not equal to j. If Aij is equal to 0 when I not equal to j, means except the diagonal, remaining all elements are 0, and also here Aij is equal to k when I is equal to j. It indicates that only the principal diagonal elements are always constant. They are going to have the same value for each and every principal diagonal. Then we are going to call this matrix as a scalar matrix. So simply here, so this, suppose if m is not equal to n, then this matrix is called as the rectangular matrix. This is not a scalar matrix. It is actually a, if suppose m is not equal to n, it indicates that if the number of rows is not equal to number of columns in a matrix, then we are going to call that matrix as a rectangular matrix. Scalar matrix means simply, what is the meaning of a scalar matrix? Scalar matrix means is simply, we can say all the non-principal diagonal elements are 0 and all the principal diagonal elements are always same. It is equal to k. Then we are going to call that matrix as a scalar matrix. If suppose for a matrix M is equal to Aij n cross n, here also still we are going to consider it as square matrix. And if Aij is equal to 0 when I not equal to j, it indicates that all the non-principal diagonal elements are 0 and Aij is equal to 1 when I is equal to j. Means whenever for a principal diagonals, if all the elements are 1, then we are going to call that matrix is a identity matrix. So simply one thing you have to remember here, suppose except principal diagonal, if remaining elements are 0, then we are going to call it as a diagonal matrix. But for a diagonal matrix, if all the elements are equal, but if they are not equal to 1, then we are going to call this as a scalar matrix. But for a diagonal matrix, if all the principal diagonal elements are equal to 1, then we are going to call that matrix as the identity matrix. So now we will go for the another one. Suppose for a matrix M is equal to Aij n cross n, and if Aij is equal to 0 when I greater than j. For I greater than j, it simply indicates that the elements are going to present below the principal diagonal. It indicates that the elements are going to present below the principal diagonal. And if the elements are, all the elements below the principal diagonal elements are 0, it indicates that all the non-zero elements are going to present above the principal diagonal. Then we can say this matrix is called as the upper triangular matrix. Means if the non-zero elements are going to present above the principal diagonal, then that matrix is said to be a upper triangular matrix. In shortcut, we are going to write it as the UTM, which is called as the upper triangular matrix. Now we will go for the another one, which is suppose for a matrix M, Aij, it's also a square matrix n by n, and if Aij is equal to 0 when I less than j. If Aij is equal to 0 when I less than j, it indicates that all the elements which are above the, means the elements which are above the principal diagonal are always 0. Then it indicates that all the non-zero elements are going to present below the principal diagonal elements. So therefore we can say this matrix is said to be a lower triangular matrix. Simply I can tell you one important thing is, if all the non-zero elements are going to present above the principal diagonal, then we are going to call that matrix as the upper triangular matrix. And if all the data non-zero elements are going to present below the principal diagonal elements, then we are going to call this as the lower triangular matrix. And suppose there is a matrix M with Aij m cross n, and if you want to do the transpose of the matrix, so the transpose of the matrix is simply we have to interchange either rows to columns or columns to rows. See, interchanging of rows to columns or columns to rows, we are going to call that matrix as the transpose of a matrix. See, if the original matrix as the order of the matrix is m cross n, then the transpose of the matrix will become n cross m. Means just we are going to interchange the rows and columns. And suppose there is a matrix M with Aij n cross n. Suppose if there is a matrix M with Aij n cross n, simply it indicates that it is a square matrix. If the number of rows is equal to number of columns, then we are going to call that matrix as a square matrix. And if Aij is equal to Aji, and if Aij is equal to Aji, it indicates that the transpose of the matrix is equal to the matrix itself. Then we are going to call that matrix as a symmetric matrix. See, for any matrix, if the transpose of the matrix is equal to the matrix itself, then we are going to call that matrix as the symmetric matrix. If the transpose of the matrix is equal to the matrix itself, then we are going to call that matrix as the symmetric matrix. It indicates that Aij is equal to Aji for all ai comma j. Then we are going to call this as the symmetric matrix. So simply for a symmetric matrix, it has to be a square matrix, and also the transpose of the matrix must be equal to the matrix itself. Then we are going to call that matrix as a symmetric matrix. Suppose for a square matrix of M is equal to Aij n cross n, but here now the reverse one, it is reverse of the previous one, which is Aij is equal to minus Ji for all I not equal to j, except I not equal to j means except diagonal, remaining everything it is going to get whole. And also Aij is equal to 0 for I comma j. It indicates that all the principal diagonal elements are 0, and always Aij is equal to minus Aj for I not equal to j. Then we can say that the transpose of the matrix is equal to, if the transpose of the matrix is equal to minus M, then we are going to call this matrix as a skew symmetric matrix. Means for a skew symmetric matrix, always the principal diagonal elements are going to be always 0. See, for a skew symmetric matrix, always the principal diagonal elements are going to become 0, and also the transpose of the matrix is equal to minus M. It indicates that Aij is equal to 0 for all the principal diagonal elements, but for non-principal diagonal elements, always Aij is equal to minus Ji. Or simply we can say the transpose of the matrix is equal to negative of the matrix, then we are going to call this as a skew symmetric matrix. If the transpose of the matrix is equal to matrix, then we say it is a symmetric matrix. If the M transpose is equal to minus M, then we are going to call it as a skew symmetric matrix. For a skew symmetric matrix, always the principal diagonal elements will be always equal to 0. But not the case for the symmetric matrix. Suppose we are going to go for the another matrix, which is a square matrix of M is equal to Aij n cross n. And if this matrix is satisfying this condition, which is M into M transpose is equal to I, or we can say go for the reverse multiplication also, which is M transpose into M. It indicates that M into M transpose is equal to M transpose into M is equal to I. If we are going to get this condition, then we are going to call this matrix is a orthogonal matrix. You see, if any matrix satisfying the condition which is M into M transpose is equal to M transpose into M is equal to identity matrix, then that matrix M is said to be a orthogonal matrix. But similarly, see the basic condition. So now you can see clearly, if you compare these two equations, you can see clearly one thing is very common, which is here M into M inverse is equal to identity matrix and M into M transpose is equal to identity matrix. So if you compare these two equations, we can simply say that M inverse is equal to M transpose. It indicates that for orthogonal matrix, the inverse of the matrix itself is equal to the transpose of the matrix. So therefore we can say M inverse is equal to M transpose for orthogonal matrix. Then we can say for orthogonal matrix, always the transpose of the matrix itself is equal to the inverse of the matrix. And also one more important thing is here always the determinant of that matrix will be always equal to 1. See, for orthogonal matrix, always the determinant of that matrix will be always equal to 1. So one thing is very much similar. So here for orthogonal matrix, always the transpose of the matrix itself is equal to the inverse of the matrix, and it has to satisfy one condition, which is M into M transpose is equal to M transpose into M is equal to identity matrix. And also the transpose of the matrix itself is equal to the inverse of the matrix, and always here the determinant of the matrix is equal to 1. These are the conditions which are going to apply for the orthogonal matrix. If any matrix is going to satisfy all these conditions, then definitely we are going to call that matrix is said to be a orthogonal matrix. And suppose there is also another matrix which is M is equal to Aij n cross n. It is also a square matrix, and here if m into m is equal to m, means if you multiply the matrix with itself and if you are going to get the same matrix, then we are going to call that matrix as the idempotent matrix. Suppose if that matrix, if you are going to multiply with its own matrix and if you do the multiplication and still you are going to get the same result, then we are going to call that matrix as the idempotent matrix. I hope you are going to understand the things which I am trying to say. So finally, if any matrix, if you are going to multiply with itself own and still you are going to get the same matrix, then we are going to call that matrix as the idempotent matrix. If any matrix satisfying this condition, which is m into m is equal to m, means if you multiply that matrix with itself and you are going to get the same matrix, then we are going to call that matrix as the idempotent matrix. So now we are going to learn about another matrix, which is the m is equal to aij n cross n. Here also it is a square matrix, but here now m to the power of k is equal to 0. It indicates that here m is a nilpotent matrix. Means suppose if you are going to multiply the matrix for k times, so after k times you are going to get a 0. Suppose if there is a matrix m and if you are going to do the multiplication m1, m2, m3, like 3 times, 4 times you are going to multiply, after a certain value of k, you are going to get a matrix as 0. So therefore we can say that matrix is said to be a nilpotent matrix. Means if any matrix satisfying the condition which is m to the power of k is equal to 0, that matrix is said to be a nilpotent matrix. Or simply we can say, if you are going to multiply the matrix up to k times, after that you are going to get the result as null matrix, then we can say that matrix is said to be a nilpotent matrix. Suppose there is another matrix which is m is equal to aij n cross n, and but here now if m to the power of k plus 1 is equal to m, it indicates that m is a periodic matrix where a k is called as a period of the matrix m. Simply here, suppose there is a matrix m. Suppose if you are going to multiply for k plus 1 times, say after k plus 1 times, still you are going to get the original matrix, then we can say that that matrix is called as a periodic matrix, means again it is going to get repeat. So therefore we can say the period of the matrix is equal to k. So k is called as a period of the matrix, and this matrix is going to repeat itself after k plus 1 time. So therefore we can say k is called as a period of the matrix. So after k, the matrix is again repeating itself. So that is the reason k is called as a period of the matrix and m is called as a periodic matrix, because it is going to repeat after the period of k. Suppose there is a matrix m with aij n cross n. Simply this is also a square matrix, but here m square is equal to I. So m square is equal to I, it indicates that m square is equal to I indicates that if you are going to multiply the matrix with itself, you are going to get a identity matrix, then that matrix is said to be a involuntary matrix. See, if you are going to multiply matrix with itself, if you are going to get a identity matrix, then that matrix is said to be a involuntary matrix. Involuntary matrix means here, as I have already told you, here m into m is called as a, if you do the multiplication of matrix m with itself, if you are going to get the identity matrix, then that matrix is said to be a involuntary matrix. But the basic condition in mathematics is here m into m inverse is equal to I. It indicates that if you multiply m inverse with m, we are going to get I. So if you compare these two equations, definitely we can say m is equal to m inverse, means the inverse of the matrix itself is equal to matrix, then that matrix is said to be a involuntary matrix. Or simply m into m is nothing but I, then m inverse is equal to m. So therefore if any matrix satisfying the condition which is m square is equal to I, then that matrix is said to be a involuntary matrix. So now we are going to learn some of the complex matrices. Now we are going to study. Suppose there is a matrix m with aij plus ibij m cross n, and if you want to do the conjugate, see conjugate of the matrix is simply here wherever there is a complex numbers, just you have to go for the inversion. If there is a 2 plus j3, 2 plus i3, if m conjugate means you have to go for the 2 minus i3. See, wherever there is a plus, you have to replace by negative. Wherever there is a negative, you have to go for the positive. Only wherever the elements there are complex numbers, you have to do this operation, and remaining places you don't have to do this operation. Just replace the complex numbers by reverse one. And the order of the matrix is still the same as the previous one. Suppose there is a matrix, complex matrix of aij plus bij m cross n. Here now m to the power of theta. See, m to the power of theta means m conjugate whole transpose, or simply we can say m transpose whole conjugate. See, m to the power of theta, there is also another notation which is m to the power of star. So therefore we can say m to the power of theta or m to the power of star. It indicates that m conjugate whole transpose or m transpose whole conjugate means first do the conjugate then transpose, or then you go for another process which is first do the transpose and then do the conjugate. You can go for the other of the process, still you are going to get the same result. So therefore m to the power of theta is equal to, just if you do these operations, finally you are going to get the result which is Aji minus Ibji n cross m. It indicates that either you go for the conjugate and transpose, or whether you go for the transpose and conjugate, then finally you are going to get some rearrangement. After that you are going to get a thing which is Aji minus Bji n cross m, means order of the matrix is going to get changed, and also the positive value will become negative of complex numbers. Suppose there is a matrix M, complex matrix M, which is Aji plus Bij n cross n. It is a square matrix. For this, always if m to the power of theta is equal to m, if m to the power of theta is equal to m, then that matrix is said to be a Hermitian matrix. If m to the power of theta is equal to m, then that matrix is said to be a Hermitian matrix. Always here Bii is equal to 0. It indicates that, see, if this condition is going to get satisfied, it indicates that all the complex terms, listen carefully, all the complex terms in the principal diagonal are always 0. It indicates that simply all the principal diagonal elements in the Hermitian matrix are always purely real. That is the meaning of this matrix, of this condition. So therefore we can say for any complex matrix, here if m to the power of theta is equal to m, then if any matrix satisfying this condition, then we are going to call that matrix as the Hermitian matrix. Hermitian matrix, it indicates that for Hermitian matrix always the principal diagonal elements are purely real, are always purely real. Suppose there is a complex matrix of m, Aij plus Ibij n cross n. It is also a square matrix of complex matrix. But here now you can see clearly here, if any matrix satisfying this condition which is m to the power of theta is equal to minus m. If m to the power of theta is equal to minus m, then if any matrix satisfying this condition, then definitely we are going to call that matrix as the skew Hermitian matrix. And definitely here Aii is equal to 0. It indicates that all the real parts of the principal diagonal elements of the skew Hermitian matrix are definitely 0. It indicates that simply all the principal diagonal elements of the Hermitian matrix are purely imaginary, whereas for a Hermitian matrix always you are going to get the pure real principal diagonal elements. But for a skew Hermitian matrix, always we can say the principal diagonal elements are purely imaginary. And for Hermitian, m to the power of theta is equal to m, and for a skew Hermitian, m to the power of theta is equal to minus m. That is the meaning or interrelation between this Hermitian matrix and the skew Hermitian matrix. And the last one, which is, suppose there is a square matrix of complex square matrix which is m is equal to Aij plus Ibij n cross n. If any matrix satisfying this condition which is m into m to the power of theta is equal to I, or we can say m to the power of theta into m, then we are going to call this matrix. If any matrix satisfying this condition which is m into m to the power of theta is equal to I, or otherwise m to the power of theta into m, then we are going to call that matrix as the unitary matrix. We are going to call that matrix as the unitary matrix. And definitely m to the power of theta is equal to m to the power of minus 1. So you can see clearly here, if m into m to the power of theta is equal to I, and another condition is m into m inverse is equal to I. So by comparing these two equations, definitely we are going to get m to the power of theta is equal to m to the power of minus 1. So therefore we can say, if any matrix satisfying this condition which is m into m to the power of theta is equal to I, or m to the power of theta into m is equal to I, then that matrix is said to be a unitary matrix, or simply we can say m to the power of theta is equal to m to the power of minus 1. Then definitely the determinant of this matrix will become, suppose if you do the determinant of this matrix, finally you are going to get, after doing the simplification, you are going to get a plus ib. And definitely, and if you do the a square plus b square, definitely you are going to get the result as 1. So always a square plus b square is equal to 1 you are going to get after doing the determinant of this unitary matrix. So if you do the determinant of this matrix, definitely you are going to get a complex number which is a plus ib, and if you do the square of this a square plus b square, definitely you are going to get the 1. So now, up to now, whatever we have learned is just we have learned the definitions of the matrices. What are definitions of different types of matrices we are going to see in this linear algebra, everything, and their properties also we have discussed in a very much detailed manner. So now let us do the summary of whatever the things we have learned up to now. See, we will now discuss each and every matrix up to now whatever we have learned, just give a few summary. If suppose the transpose of the matrix, if the transpose of the matrix itself is equal to that matrix, then we are going to call that matrix as a symmetric matrix. But if the transpose of the matrix is equal to negative of that matrix, then we are going to call that matrix as the skew symmetric matrix. And also m into m transpose is equal to I. If m into m transpose is equal to I, then that matrix is said to be orthogonal matrix. Or simply we can say the inverse of the matrix itself is equal to the transpose of the matrix, or simply the determinant of that matrix will be equal to 1. These are the conditions of the orthogonal matrix. And if you do the multiplication of the matrix with itself, and if you are going to get a matrix, same matrix, then that matrix is said to be an idempotent matrix. Means m into m is equal to m, then that matrix is said to be an idempotent matrix. Suppose if for a matrix, if m to the power of k is equal to 0, means after certain multiplication of k, if you are going to get a 0 matrix, then that matrix is said to be a nilpotent matrix. And suppose there is a matrix m, and if you do the multiplication up to k time, after that if you go for the other multiplication, still you are going to get the original matrix, then we can say simply that matrix is said to be a periodic matrix, and k is called as a period of the matrix. But if there is a matrix m, and if you do the square of that matrix, still you are going to get the idempotent matrix, or we can say you are going to get the identity matrix, then that matrix is said to be a involuntary matrix. So for involuntary matrix, the condition is m inverse is equal to m. And also if m to the power of theta is equal to m, then we are going to call that matrix as the Hermitian matrix, where m to the power of theta is equal to m transpose whole conjugate or m conjugate whole transpose. You can do either of these, still you are going to get the same result. Then that matrix is said to be a Hermitian matrix. See, for a Hermitian matrix, I have already told you, for a Hermitian matrix always you can say, for a Hermitian matrix always the principal diagonal elements are purely real. Suppose if there is a matrix which is going to satisfy this condition, which is m to the power of theta is equal to minus m, then we say that matrix is said to be a skew Hermitian matrix. Then that matrix is called as a skew Hermitian matrix. It indicates that I have already told you, means for a skew Hermitian matrix, definitely the principal diagonal elements are purely imaginary. And also for a skew symmetric matrix, I have already told you the principal diagonal elements are purely 0. Now the last one is, if any matrix satisfying this condition, which is m into m to the power of theta is equal to I, then we are going to call that matrix as the unitary matrix. Or simply we can say for unitary matrix, the m inverse is equal to m to the power of theta, and the determinant of the matrix you are going to get a complex number which is a plus ib, and always a square plus b square is equal to 1. So these are the conditions of the unitary matrix. So now we have learned about the different types of matrices, their properties, their conditions we have learned. So now we'll discuss about the properties of the diagonal matrix. See, the properties of the diagonal matrix now we are going to learn. See here, suppose there is a diagonal matrix of elements which are going to consist the x, y, z. Suppose this is a 3 by 3 matrix, and these are the x, y, z. So therefore, there is also another diagonal matrix of p, q, r. It indicates that these are going to present in a diagonal. And if you do the addition, means you are going to add the corresponding elements. So still you are going to get a diagonal matrix of the diagonal elements are x plus c, x plus p, y plus q, and z plus r. Simply we are going to add the corresponding diagonal elements. Suppose if you are going to do the multiplication of the two diagonal elements, the diagonal elements are x, y, z, and diagonal elements are the p, q, r. If you are going to multiply these two matrices, then finally you are going to get diagonal matrix. Just you have to do the cross multiplication of the corresponding diagonal element, which is diagonal matrix of p into x, q into y, and also z into r. So these are the matrix you are going to get. It simply indicates that we have to go for the multiplication of the corresponding two diagonal elements. Suppose if you are going to do the inverse of a diagonal matrix, it indicates that you are going to get a new diagonal matrix. Just you have to interchange, or you can say you have to go for the reciprocal of the diagonal elements. If the initially it has x, y, z means now it will become 1 by x, 1 by y and 1 by z. Suppose if you are going to the transpose of a diagonal elements means the matrix is not going to get changed. It will be same as the previous one, which is diagonal of x comma y comma z. Suppose there is a diagonal matrix of x comma y comma z, and if you are going to do the multiplication of up to n times, then definitely here each and every corresponding diagonal element will become n times. So therefore we can say x to the power of n, y to the power of n and z to the power of n. This is the matrix you are going to get finally. Suppose what is the eigen values of a diagonal matrix? See, for a diagonal matrix of x comma y comma z, then what are the eigen values? See, eigen values are itself the diagonal elements of a diagonal matrix. So for a diagonal matrix always, and we can say for upper triangular matrix or for lower triangular matrix or for the diagonal matrix, always the eigen values are the diagonal elements itself, which are the x comma y comma z itself. These are the eigen values. And if you want to find the what is the determinant of a diagonal matrix, simply the determinant of any matrix itself is equal to the product of the product of the eigenvalues, but the eigenvalues are x comma y comma z, so therefore you have to go for the multiplication of the eigenvalues, which is x into y into z. It is also called as the multiplication of the diagonal elements, so therefore x into y into z. So now we have learned some of the important properties of a diagonal matrix, means how we are going to do the addition, how we are going to do the multiplication, how we are going to do the inverse, transpose and also multiplication up to n times, and also we have learned about the eigenvalues and also determinant of the diagonal matrix. All these things now we have learned. So now we will discuss about the properties of the identity matrix. So for identity matrix, what are the properties? Now we are going to see. Suppose A into I is equal to I into A is equal to A. It indicates that for any matrix, if you are going to multiply the identity matrix either in the any fashion, in the forward fashion or the reverse fashion, means A into I is equal to I into A is equal to A. It indicates that if you multiply any identity matrix to any other matrix, still you are going to get the original matrix as the A. So therefore A into I is equal to I into A is equal to A. So if you multiply any identity matrix to any other matrix, still you are going to get that matrix only. So therefore A into I is equal to I into A is equal to A. But if you go for n times, means I square, I cube, I 3, I to the power of 4, if you go for any number of times, still you are going to get the same matrix as the identity matrix. And also the inverse of the identity matrix itself is equal to identity matrix, so therefore I inverse is equal to I. And also the determinant of the identity matrix will be always equal to 1, because for identity matrix the diagonal elements are 1, so therefore if you multiply all the principal diagonal elements, then 1 into 1 into n up to n times, still you are going to get the 1, so therefore we can say the determinant of identity matrix is equal to 1. So simply A into I is equal to I into A is equal to A, and also I to the power of n is equal to I, and I inverse is equal to I, and also the determinant of the identity matrix is equal to 1. So these are the properties of the identity matrix. So now we discuss the properties of multiplication of a matrix by a scalar P comma Q comma K. See, suppose now we are going to discuss about some of the properties of multiplication of a matrix by scalar P comma Q comma K. See, where P comma Q comma K are scalar numbers, means 1 comma 2 comma 3 like this, pure numbers. See, what is the properties of these on the multiplication of matrix? Now we are going to see. Suppose there are matrix A and B. A and B are the matrices, and if you are going to do the addition, and then you are going to multiply a scalar number K. K is a scalar number, just a pure number. So therefore, here K of A plus B is equal to, you can take the inside, so K into A plus K into B. So for any scalar number K, you can go for either, you can take this K to the inside also. So K of A plus B is equal to K into A plus K into B. And there are two scalar numbers P and Q, and you are going to do the addition, and then you are going to do the multiplication with respect to A. So P plus Q into A is equal to P into A plus Q into A. So P is called as scalar number and Q is also scalar number. So you can go in this process also. But here P of Q of A, P, Q are the scalar numbers. So you can go for either of the fashion P into Q or Q into P. So definitely you are going to get the same thing. So therefore P into Q of K also, you can go either in this fashion or in this manner. Still you are going to get the same result. See, here minus K into A. See, you can take minus as a common. So take it outside. So minus of K into A. And also you can go for another fashion, which is K into of minus A. So you can go in any other mode, still you are going to get the same result. So therefore we can say here, these are the different way of doing the multiplication you can do by the scalars and still you are going to get the same result. So k of a plus b is equal to k into a plus k into b, p plus q into a is equal to p into a plus q into a, and p of q into a is equal to p into q of a, or minus k of a is equal to minus of k into a, or k of minus a. So you can go by any other mode, still you are going to get the same result. So now we'll discuss some of the properties of conjugate of a matrix. So what are the properties of conjugate of a matrix we are going to see? See, the conjugate of a matrix means A bar. So now we will see the different ways of properties of conjugates now we are going to see. See, A conjugate whole conjugate means still you are going to get the same original matrix, which is A, and A plus B whole bar is equal to, see, A plus B whole bar is equal to A bar plus B bar. This is the conjugate. These are the not the AND gates or the OR gates. This is only for mathematics. This is not for the digital electronics. For that it is a different. So therefore here conjugate of A plus B is equal to conjugate of A plus conjugate of B. And conjugate of K into A is nothing but here K, sometimes it can be a complex number. So it can be any complex number. So it is always necessary to do conjugate of both these. So K conjugate into A conjugate. So therefore sometimes K can be a complex number or real number. If it is a real number means you are going to get the same result after doing the conjugate, but for a complex number it is going to get interchange. Plus will become minus and minus will become plus for a complex number. So therefore A into B whole conjugate is equal to A conjugate into B conjugate. See, these are the formulas which are going to be useful only for mathematics, but for digital electronics this will be different. So that things we are going to see in the digital electronics. But now, as for now, only these formulas are very much useful. So therefore we can say A conjugate whole conjugate is equal to A, and A plus B whole conjugate is equal to A conjugate plus B conjugate, and K into A whole conjugate is equal to K conjugate into A conjugate, and A into B whole conjugate is equal to A conjugate into B conjugate. You can go for either of these things, you are going to get the same result. And suppose if A bar is equal to A only when A is the real matrix, yes. If whenever the matrix is a real matrix means not even any element in it is a imaginary, means all the elements in the matrix are purely real. So if you do the complex conjugate, still you are going to get the same matrix. So therefore A conjugate is equal to A only if all the elements in that matrix are purely real. But if it is equal to minus A when A is a purely imaginary matrix, means in that matrix if each and every element is imaginary, then definitely you are going to get A bar is equal to minus A. Means A bar is equal to A when the matrix is a purely real matrix, and A bar is equal to minus A when that matrix is a purely imaginary matrix. Then only you are going to get, these are the conditions you are going to get. And so now we will discuss some more properties of this theta. So a to the power of theta whole to the power of theta is nothing but again you are going to get the same matrix A, and these are operations are same as the complex conjugate process methods. So the properties of this theta is same as the complex conjugate. So A plus B whole to the power of theta is equal to same A to the power of theta plus B to the power of theta, and also A into B whole to the power of theta is equal to B to the power of theta into A to the power of theta. Now it is a reverse one, but for there AB whole conjugate is equal to A conjugate into B conjugate, but here it is a different. AB whole to the power of theta is equal to B to the power of theta into A to the power of theta, and also here K into A whole to the power of theta is equal to K conjugate into A to the power of theta. Sometimes K can be a complex number. So these are the two things only they are going to change. Remaining everything is same. So therefore A to the power of theta whole to the power of theta is equal to A, and A plus B whole to the power of theta is equal to A to the power of theta plus B to the power of theta. Whereas A into B whole to the power of theta is equal to B to the power of theta into A to the power of theta, and also K into A whole to the power of theta is equal to K conjugate into A to the power of theta, where K can be any complex number. So now we are going to discuss about the operations on matrices. So what are the different types of operations which are going to occur on the matrices? Now we are going to learn in a very detailed manner. The first one is the addition. Suppose now I will tell you about the addition operation. Suppose there are two matrices. See, whenever if you want to do the addition or subtraction of two matrices, definitely their order should be same. Suppose if the matrix A is of order m by n, then definitely then the matrix B should be also of the order of the n by n. Then only we can go for the addition or the subtraction. If you do the addition of the two same order matrices of m cross n, then you are going to get the resultant matrix C of order m cross n. So therefore you can say if Aij is the element on matrix A and Bij is the element of matrix B, then Cij is equal to, just you have to add the corresponding elements, which is Cij is equal to Aij plus Bij. And similarly here always the addition is a commutative property, means the addition is going to satisfy the commutative property, which is a plus b is equal to b plus a. So therefore we can say this addition is going to satisfy the commutative property, which is a plus b is equal to b plus a. And also here this matrix addition is also going to satisfy the associative property, which is a plus of b of plus c is equal to a plus of b plus c. It indicates that if you add the two matrices a plus b and then later you are going to add the c is equal to adding of the matrix b plus c and then you are going to add the matrix a. So this is called as the associative property, and this matrix addition is going to satisfy both the commutative property and also the associative property. And now k plus a is equal to k into a is equal to a plus up to k times. See, ka is equal to a plus, we have to go for the addition up to k times we need to add. See, k is nothing but k into a, where k is called as the scalar number. So k into a is equal to adding the matrix a for n for k times, that is called as a k into a. So k into a is equal to adding the matrix a for k times, or simply we can say you need to multiply the k for each and every element which is going to present in the matrix A. And now we are going to learn about the multiplication. So now we are going to learn about the multiplication properties. See, in the multiplication properties, suppose there is a matrix A of order m cross r and the matrix B as of order r cross n. So you can see clearly here, you can see if the matrix multiplication is possible only, the matrix multiplication is possible only when the number of column of matrix A should be equal to the number of rows of matrix B. See, here R is called as the column of A and here R is the row of the B. So therefore the number of columns of the matrix A must be equal to the number of rows of matrix B, then only you can do the multiplication of two matrices. So therefore A into B is equal to C. So therefore here the row of the number of rows of matrix A is m and the number of columns of matrix B is n. So then the resultant matrix will become m cross n. So therefore you can say where m is the order of the matrix C and n is the, see, m is the number of rows present in the matrix C and n is the number of columns present in C. So therefore we can say A into B is equal to C, or simply we can say Cij. See, the any element and any element in matrix C is equal to, it is sigma k is equal to 1 to r aik into bkj. See, here I is called as ith row and j is called as a jth column. Means if you want to find any element, see, the meaning of this one is if you want to find any element in matrix C, it indicates that where I is called as a, you have to take the ith row in the matrix A and you have to take the jth column in the matrix B, and then you have to add the corresponding elements to get the element Cij. So listen carefully, this indicates that this whole equation is going to tell you, suppose if you want to know what is the Cij in any matrix C element, means you have to take the ith row of the matrix A and jth column of the matrix B, and if you do the corresponding multiplication you are going to get the element Cij, where I indicates the ith row and j indicates the jth column, where you see here A is nothing but the ith row and bj is nothing but the kth column, so jth column. So if you do the multiplication of these two corresponding elements, you are going to get the element of Cij. And also here, but A into B is not equal to B into A, but sometimes it is equal. See, always generally A into B is never equal to B into A, but only some special conditions, then A into B is equal to B into A, but generally A into B is never equal to B into A, but at some special conditions only this A into B is equal to B into A. But generally we can say A into B is never equal to B into A. So simply we can say this matrix multiplication is never satisfying the commutative property. So therefore we can say this matrix multiplication is not satisfying the commutative property. And also A into B bracket of C is equal to A of B of C. So therefore we can say A into B of C is equal to A of B into C. Yes. So therefore we can say this is the associative property. Associative properties satisfy the matrix multiplication but not the commutative property. So A into B of C is equal to A of B into C. You can go for any of the things, but the matrix multiplication is satisfying only the associative property but not the commutative property. And also A into I is equal to I into A is equal to A. This I have already told you. If you multiply I into matrix with any other matrix, suppose Let me take a matrix A, then the resultant is nothing but A. So therefore A into I is equal to I into A is equal to A. And also A into A inverse is equal to A inverse into A is equal to always an identity matrix. See, then we can say that the inverse is going to exist. See, any matrix inverse is going to exist only when the determinant of that matrix is not equal to 0. Otherwise, the inverse of the matrix is not going to exist. See, if the determinant of the matrix is not equal to 0, then that indicates that we can say that inverse is going to exist. Otherwise, if determinant is equal to 0, it indicates that never the inverse is not going to exist. See, if determinant of a matrix A is equal to 0, means we can say that matrix is said to be a singular matrix. Singular matrix means if the determinant of that matrix is equal to 0, then we say that matrix is said to be a singular matrix. If the determinant of that matrix is not equal to 0, then we say this matrix is said to be a non-singular matrix. These are the very important definitions. If the determinant is equal to 0, then we say that matrix is said to be a singular matrix. Otherwise, we say it is a non-singular matrix. And also, A into B into C whole inverse is equal to A into B into C whole inverse is equal to, you have to go for the reverse process, which is C inverse into B inverse into A inverse. Suppose if you want to know what is the A into B whole inverse, which is equal to B inverse into A inverse. Suppose if you want to know A into B into C whole inverse, which is equal to C inverse into B inverse into A inverse, just you have to go for the reverse process. Then you are going to get these things. So therefore, finally, A into B whole inverse is equal to B inverse into C inverse. So therefore, these are some of the important properties of multiplication. So simply we can say that addition, see, the addition property is going to satisfy both the commutative property and the associative property, but the multiplication is not going to satisfy the commutative property, but it is going to satisfy only the associative property. So now we will discuss about the properties of transpose properties. So now we will discuss some of the important properties of transpose. See, A transpose whole transpose is equal to, see, A transpose whole transpose is equal to A, and also A plus or minus B whole transpose is equal to A transpose plus or minus B transpose. If K into A of transpose is equal to, you can take the K inside, so K into A whole transpose. So therefore, K into A whole transpose is equal to, you can take the K outside, so K into A transpose. And ABC whole transpose is equal to C transpose into B transpose into A transpose. So you can say clearly, this transpose is going to satisfy the inverse properties also, because A into B into C whole inverse is equal to C inverse into B inverse into A inverse. In the same fashion, A into B into C whole transpose is equal to C transpose into B transpose into A transpose. So now we'll discuss some of the properties of the trace. See, trace is nothing but, see, trace means, suppose there is a matrix. So for a matrix, for a square matrix, definitely there will be principal diagonal. If you add each and every element of the principal diagonal, the summation you are going to get, the resultant is called as a trace of a matrix. Suppose there is a square matrix of A, Aij and cross n. Then the trace of A is equal to, just we have to add each and every element present in the principal diagonal, or simply we can say sigma of Aii. So now we will discuss the transpose properties. See, transpose of A plus or minus B is equal to transpose of A plus or minus of transpose of B. And transpose of lambda into A, lambda is a scalar quantity, so you can take the lambda outside. So lambda into transpose of trace of A. And trace of A into B is equal to trace of B into A. So therefore, trace of A into B is equal to trace of B into A. So therefore, no matter whether you go for A into B or B into A, the trace will be always same. So therefore, we can say trace of A plus or minus B is equal to trace of A plus or minus trace of B. Trace of lambda into A is equal to lambda of trace of A, and trace of A into B is equal to trace of B into A. So you can go by either of this process, definitely you are going to get the same solution. So now we will discuss about the determinant. So now we will discuss some of the important properties of the determinant of a matrix. Suppose there is a matrix. See, determinant is only, it is going to do, we are going to do the determinant only for a square matrix, but not for a rectangular matrix. For a square matrix, the number of rows is equal to number of columns, but for a rectangular matrix, the number of rows is not equal to number of rows. So this determinant is going to do, we are going to do the determinant only for a square matrix. So A is equal to Aij n cross n. Suppose, see, let me assume a matrix only of one element. Suppose A1 is equal to A1, small a1. Then what is the determinant of this matrix A1, which is equal to A1 itself, because there is only element A1. Suppose there is a 2 by 2 matrix. Suppose that the 2 by 2 matrix of A1, A2, A3, A4, then what is the determinant of this 2 by 2 matrix? Which is, we have to go for the multiplication of A1 into A4 minus A2 into A3. So corresponding diagonal elements you need to multiply and then you have to take the subtraction. So A1 into A4 minus A2 into A3. See, this is for the only single element. Suppose if a matrix has only one row, one column, then the determinant of the matrix itself is equal to the number. Either it can be positive or negative. So therefore we can say, suppose, see now let me tell you the difference. Suppose if you want to go for the determinant of more than 2 by 2 matrix, then definitely you need to know some important things, which are the cofactor of an element Aij. See, this cofactor of an element Aij is very much important to find the determinant of any matrix. Suppose if you want to find what is the cofactor of an element Aij, which is -1 of I plus j into minor of element Aij. See, it indicates that, see, suppose if you want to know what is the cofactor of an element Aij, which is equal to -1 over the power of I plus j into minor of element Aij. See, minor of element Aij means we have to eliminate that row and also that column of that element. Then what you are going to get, the remaining matrix, whatever you are going to get, you have to find the determinant of the remaining matrix. That is called as the minor of an element Aij. So listen carefully, minor of an element Aij means you have to eliminate from the original matrix that row and that column. See, whatever the matrix you are going to get later, that you need to take the determinant of that matrix. That is called as the minor of an element Aij. So therefore, cofactor of an element Aij is equal to -1 over the power of I plus j into minor of element Aij. So therefore now, see, suppose there is a 3 by 3 matrix. Suppose there is a 3 by 3 matrix. See, now I want to find what is the determinant. So determinant of the matrix A is equal to sigma k is equal to 1 into n, sigma k is equal to 1 to n, aik into aik. See, listen, suppose first you have to do is, first there is a matrix, and also now you have to find each and every cofactor of each and every element of that matrix. So therefore you are going to get the cofactor also you are going to get. Then what you are going to do is very simple. See, suppose there is a 3 by 3 matrix. Suppose there is a 3 by 3 matrix. The matrix is going to contain the elements A11, A12, A13 and A21, A22, A23 and A31, A32 and A33. See, now I want to find what is the cofactor of each and every element. So after finding this cofactor of each and every element, finally I am going to get a matrix which is A11, A12, A13, A21, A22, A23 and A31, A32 and A33. So these are the capital letters and these are the small letters. Suppose if you want to know what is the determinant of this matrix, then definitely, suppose if you take the first row, suppose if you are going to take the first row, then you also have to take here the first row also. Of the cofactor matrix also you need to take the first row. So therefore, A11, small a11 into capital A11, small a12 into capital A12 plus small a13 into capital A13. So like this you have to go corresponding elements you need to multiply and then you need to add. Then you are going to get the overall determinant of that matrix. So simply we can say small a11 into capital A11 plus small a12 into capital A12 plus small a13 into capital A13. Suppose if you are going to take the second row, then here also you need to take the same second row. So therefore small a21 into capital A21 plus small a22 into capital A22 plus small a23 into capital A23. Otherwise you can go for the third row. If you are going to take the third row in the matrix, here also in the cofactor matrix also you need to take the third row. So therefore small a31 into capital A31 plus small a32 into capital A32 plus small a33 into capital A33. See, same thing I have written here. So therefore if you are going to take the row, then if you are taking the rows in the matrix, similarly you have to take the rows in the cofactor matrix also. But if you are going to take in the reverse manner, suppose if you are taking the first row, in this matrix, but you are taking the second or third, then definitely if you do the corresponding elements multiplication and addition, finally you are going to get that 0. So that is the reason I have told you here aik, it indicates that it is a ith row and here also same ith row. Here ai means same ith row and here also same ith row. So therefore you need to take the same ith rows and you have to do the corresponding elements multiplication and then overall you need to do the addition. Suppose if you are taking the column, then definitely here also you have to take the same column. If you are taking the first column means here also you have to take the first column. Suppose if you are taking the second column here means here also you have to take the second column. But if in this case, suppose if you are taking the third column, here also you need to take the third column. So same thing I have written here. So therefore we can say here, then finally we are going to get, see, small a11 into capital A11 plus small A21 into capital A21 plus small 31 into A31 into capital A31. Similarly, small A21 into capital A21 plus small A22 into capital A22 plus small. Suppose if you are taking the first column here, you also have to take the first column. So A11 into A11 plus A21 into A21 plus A31 into A31. Similarly, A12 here, you have to take the A12 into A12 plus A22 into A22 plus A32 into A32. Similarly, here A13 into A13 plus A23 into A23 plus A33 into A33. So only thing is you have to take the corresponding. Suppose if you are taking the row, then you have to take the row in this cofactor matrix also. But if you are taking the column, this matrix, then definitely you have to take the column here. So always you have to multiply the corresponding row and the corresponding row, then only you are going to get the result of determinant. But if you are taking the reverse process, which is first row and the second row, then you are going to get the 0. So therefore we can say, here you can see clearly here, so we can say jth column of matrix A and jth column of the cofactor matrix, and if you are doing the corresponding multiplication, and then overall you are going to do the addition. So therefore kj is nothing but column elements of jth column of A, and here kj is nothing but column elements of jth column of cofactor matrix A. But here aik indicates that row elements of the ith row of A, and aik is nothing but row elements of the ith row of the cofactor A. So therefore what I am trying to say finally is, suppose if you are taking the first row in this matrix, then here also you have to take the first row and you have to add the corresponding elements and do the addition. But if you are taking the first row and the second row here, if you do the cross multiplication and then you do the addition, finally you are going to get the 0. The same thing I have written here. Suppose there is aik. See, aik is nothing but ith row, but here p is a pth row. So ith row of the matrix A and pth row of the cofactor matrix A, if you do the corresponding elements multiply and then take the overall addition, you are going to get 0. Here p is not equal to I. So p can lie between 1 to n, because n is the order of the matrix. So therefore p can lie between 1 to n. And now because it's a square matrix, so n by n. And similarly here j is nothing but jth column of matrix A, and here pth column of matrix cofactor matrix A, and if the cross multiplication, if they are not equal, then definitely you are going to get 0. So where p is lies between 1 to n, because here matrix A is a square matrix, the order of the matrix is n to n cross n, so therefore p can lie between 1 to n. So therefore we can say clearly, if you are not taking the corresponding rows or corresponding elements, then their multiplication and summation will become 0. That is the reason always this procedure of finding the determinant, you have to go for the same row and the same row. Suppose if you are taking the same rows of matrix A and cofactor matrix and do the cross multiplication and do the addition, you are going to get the result. Now we are going to discuss about the elementary transformations. See, now we will discuss about the elementary transformations. Means this transformation means how we are going to interchange the rows and columns. How we are going to interchange the rows and columns. How it is going to affect the determinant of a matrix and the rank of the matrix. Now we are going to see. See, Rij indicates that interchanging the two rows. Means Rij indicates that we are interchanging the ith row and the jth row. So if you do the Rij is nothing but interchanging two rows which are the I and j. Cij means interchanging two columns of I and j. Suppose Cij means we are going to interchange the ith column and also jth column. Rij means interchanging the ith row and the jth row, but Cij indicates that it is interchanging the ith column and the jth column. See, this transformation changes the determinant of the new matrix form. So if you go for this elementary transformation, if you are going to interchange either two rows or two columns, definitely this transformation is going to change the determinant of a matrix, but it is not going to change the rank of the matrix. This we are going to learn in the coming classes. So therefore we can say here, if you are going to interchange the two rows or two columns, definitely whatever the new matrix which we are going to get, this new matrix will have different determinant, means it is going to be changed. So therefore this transformation is going to change the determinant of the new matrix form. So therefore the matrix whatever you are going to get new is equal to -1 over the power of k into determinant of the original matrix. So therefore the determinant of the new matrix form is equal to -1 over the power of k into determinant of the original matrix, where k indicates that these many times the transformation is done. See how many times you are going to do this process for the original matrix. If you are going to do this process only one time, then you have to take k is equal to 1. But if you are doing it twice, then you have to take k is equal to 2. So it indicates that how many number of times you are going to do the transformation for a matrix. So the determinant of the new matrix is equal to minus 1 over to the power of k into the determinant of the original matrix, where k indicates that this many number of times you are going to do the transformation for the given matrix. So this is the first type of interchange you are going to learn. But now we are going to learn about the another type of transformation, which is Ri. Suppose if you are going to replace rth row, this ith row by b into Ra plus k into Rj plus so many number of times. Suppose if you are going to replace ith row by this many number of transformations like b into Ra plus k into Rj so many number of times, means if you are going to take the remaining rows and if you do the addition or subtraction to this original row, then you are going to get a new row which is Ri. Otherwise you can go for the column also. You can replace a column by any other addition or subtraction with the remaining column elements with the original one. So therefore b into Ci plus k into Cj up to so many number of rows, means if you are going to replace the ith row, which is ith row, if you are going to replace by remaining other element rows by doing some addition or subtraction with that matrix, with that row, and you are going to get a new row that we are going to call it as the Ri or Ci. So therefore this is for the row and this is for the column. So this transformation won't change the determinant of the new matrix form. So this is called as the second transformation. So the first transformation is going to change the determinant of the matrix, but the second transformation is not going to change the determinant of the matrix. So only the first transformation is going to change determinant of the matrix, but not the second transformation. So the first transformation means only we are going to interchange 2 rows or 2 columns, but the second transformation is you are changing the ith row by doing the additional subtraction with the other rows with the original one. Then we are going to get a new row or new column, that is called the second transformation. For this transformation, the determinant of the matrix will never change. And some more properties also we are going to learn. See, always the determinant of the matrix is equal to determinant of the transpose of the matrix, means by doing the transpose of matrix, two things are not going to change, which is the rank of the matrix and also determinant of the matrix. These two things are not going to get changed. So remember one thing, that the determinant of the matrix of A is equal to determinant of the transpose of the matrix, but the rank of the matrix also not going to get changed by doing the transpose. All the elements, if all elements of any row or any column are 0, then we get the determinant of the matrix A is equal to 0. See, suppose if you take any matrix, in that matrix, if each and every row, we can see if you take any row, in that row if all the elements are 0, or if you take any column, in that column if all the elements are 0, then definitely we can say the determinant of that matrix will be equal to 0. Because already we have learned about the determinant concept. So with the help of the determinant concept, if you take any ith row, then you have to take the ith row of the cofactor of the matrix. But ith row of the matrix itself are 0. So therefore no matter whatever the cofactor, definitely if you do the cross multiplication, definitely you are going to get the 0. So therefore if a matrix which is going to have any row which is full of zeros or any column which is full of zeros, then definitely we can say that determinant of that matrix itself is equal to 0. If 2 rows or 2 columns are identical, or multiple of each other, then determinant of that matrix is 0, which is determinant of that matrix A is equal to 0. It indicates that suppose if there are 2 rows or 2 columns are identical or multiple of each other, then the determinant of that matrix is 0. See, suppose in a matrix, if you have any 2 rows or 2 columns which are identical or which are multiple of each other, then we can definitely say the determinant of the matrix is equal to 0, because by using the second transformation, we can get a matrix of total column 0 or total row 0. So therefore we can say by using the second transformation, the determinant of the matrix is not going to get changed. So therefore we can say we are going to get it 0, because that row itself is full of zeros or column is full of zeros. So therefore the determinant of the matrix is equal to 0. So therefore we can say simply, if any matrix which is going to have 2 rows or 2 columns which are identical to each other or multiple of each other, then definitely we can say the determinant of that matrix is equal to 0. If only one row or one column is multiplied by k, then determinant of the new matrix is equal to k times of the determinant of the original matrix. Suppose if only one row or one column is multiplied by k, then determinant of the new matrix is equal to k times the determinant of the original matrix. See, suppose if you take a matrix A, for that matrix, suppose one row, only for one row, I multiplied by k for each and every element in that matrix. So therefore, whatever the new matrix which I am going to get, it is k times the determinant of the original matrix. Suppose if p rows or p columns are multiplied by k, then we get, see, if p rows or p columns are multiplied by k, then what we are going to get? See, p rows or p columns are multiplied means k, we are multiplying by p rows, so therefore k into k up to p times. So therefore k to the power of p into determinant of the original matrix, where p is less than or equal to n, because here p rows are nothing but the number of rows, because the matrix itself has a order n by n. So the rows should be always less than or equal to n. So therefore p always less than or equal to n. So therefore we can say if p rows or p columns are multiplied by k, then definitely the determinant of the new matrix is equal to k to the power of p into a determinant of the original matrix, where p is nothing but the number of rows which are multiplying by k, which is always less than or equal to n, because n is the order of the matrix. Till a small properties, which is the determinant of a into b is equal to determinant of a into b is equal to determinant of a into the determinant of b. See, it's a very much important formula, which is determinant of a into b is equal to determinant of a into determinant of b. And if you want to know what is determinant of a square, see, determinant of a square is equal to determinant of a into determinant of a, which is determinant of a whole square. So therefore determinant of a square is equal to determinant of a whole square. Suppose if you want to go for a to the power of n, means you have to go for n times. So therefore determinant of a into determinant of a up to n times, or simply we can say determinant of a whole to the power of n. But if n is equal to 1, if n is equal to minus 1, substitute here, you are going to get determinant of a inverse is equal to 1 by determinant of a. So therefore we can say determinant of a to the power of n is equal to the determinant of a whole to the power of n. So therefore if you in place of n substitute minus 1, so you are going to get determinant of a to the power of minus 1 is equal to 1 by determinant of n. And also we can say adjoint of matrix A. See, the determinant of adjoint of matrix A is equal to determinant of A whole to the power of n minus 1, where n indicates the order of the matrix. So listen carefully, this form is very much important, which is determinant of adjoint of matrix A is equal to determinant of A whole to the power of n minus 1. Suppose if you want to know what is the determinant of the adjoint of A is equal to determinant of A whole to the power of n minus 1 whole square. See here, there are two adjoints, so you have to go for the square, but here there is only one adjoint, so n minus 1 whole to the power of 1. So listen carefully, if there are two adjoints means you have to do the square, if there is only one adjoint means you have to go for n minus 1 whole to the power of 1. So therefore determinant of adjoint of A is equal to determinant of A into whole to the power of n minus 1. Determinant of adjoint of A is equal to the determinant of A whole to the power of n minus 1 whole square, because there are two adjoints, so you have to go for the square. If there is only one adjoint means you have to go for the 1, which is n minus 1 whole to the power of 1. For unitary matrix, I have told you everything about the unitary matrix. For unitary matrix, the condition is A into A to the power of theta is equal to I, or we can say A to the power of theta into A is equal to I, means A to the power of theta must be equal to A inverse. See, I have already told you A to the power of theta is nothing but A conjugate whole transpose or A transpose whole conjugate. See, suppose there is a matrix A which is Aij n cross n, or simply we can assume this matrix is a complex matrix. See, now after doing the determinant of that matrix, you are going to get a complex number which is A plus IB, and if you take the A square plus B square and if you do the sum, definitely you are going to get as a 1. So this is the importance, or you can say this is the beauty of the unitary matrix. So if any matrix satisfying this condition, which is A into A to the power of theta is equal to I, then we can say that matrix is said to be a unitary matrix. If matrix is a triangular matrix, then we get determinant of A is equal to product of the diagonal elements. See, I have already told you for triangular matrix, whether it can be upper triangular matrix or the lower triangular matrix, or whether it can be diagonal matrix, always the eigenvalues are the diagonal elements itself. So therefore we can conclude that the determinant of the matrix itself is equal to the product of the eigenvalues as the eigenvalue itself for the diagonal elements. So therefore the determinant of the matrix A is equal to the product of the diagonal elements. If matrix is an orthogonal matrix, then we get the determinant of the matrix is equal to 1. See, orthogonal matrix I already told you, which is A into A transpose is equal to I. See, if any matrix satisfying this condition, which is A into A transpose is equal to I, then we can say that matrix is said to be an orthogonal matrix, means A inverse is equal to A transpose. So therefore, that matrix always, the determinant value will be always equal to 1. That is the beautiness of the orthogonal matrix. So for always the orthogonal matrix, always the determinant of that matrix will be always equal to 1. Suppose if P rows or P columns are multiplied by K1, K2, Kp, then what you are going to get? Suppose there is some matrix. For this matrix, for the first row, you are multiplied each and every element by K1, and the second row you are multiplied by K2, and the third row you are multiplied by K3, and up to Pth row you are multiplied by Kp. Then what is the determinant of the new matrix which is you are going to get? Which is determinant of new matrix is equal to K1 into K2 into up to Kp into determinant of the original matrix. So therefore we can say that determinant of the new matrix is equal to K1 into K2 into up to Kp into determinant of the old matrix. Like this you are going to get. So this is the way that you need to remember, because from this stuff definitely you are going to get questions which are of very much important. Now we'll discuss about the rank of a matrix. See, now we'll discuss the important concept of all this is rank of a matrix. See, rank of a matrix it indicates that, see, rank means, for any matrix, the rank means the number of independent rows or independent columns. For a matrix, there will be some independent rows or independent columns. The number of independent rows or independent columns, that we are going to call it as the rank of a matrix. See, suppose there is a matrix of Aij n cross n, m rows and n columns, because rank can exist for any matrix, whether square matrix or rectangular matrix, definitely you are going to get a rank. So therefore, the rank of matrix A will be less than or equal to minimum of n comma n. See, always is a very important condition. The rank of matrix A will be always less than or equal to minimum of the m comma n, where m comma n are the row, number of rows and number of columns of matrix A. So the rank of matrix A will be always less than or equal to minimum of the m comma n. Suppose the rank of matrix A is R if at least any one of the submatrix of order R have determinant non-zero and above order are compulsory 0. See, suppose, listen carefully, this point going to tell you that, suppose there is a matrix. For that matrix, suppose I am going to assume that the rank of the matrix is R. So therefore we can say then that determinant of this submatrix means of order R by R. If you take R by R order of any matrix of submatrix of overall matrix, then definitely at least one submatrix will be definitely the determinant will be always not equal to 0. But if you go for extra above R plus 1 cross, then definitely your R plus 2 comma R plus 2 order, definitely what you are going to get is more than R. For if you take any submatrix, definitely the determinant will be always equal to 0. So therefore we can say if a matrix is said to be rank R as said to be a rank, then definitely if you take any submatrix of order R, then definitely at least one of the submatrix determinant will be not equal to 0, and above that always the determinant will be always equal to 0 no matter whatever the submatrix order. The number of linearly independent row vectors or column vectors is called as the rank of a matrix A. See, I have already told you this point, which is the number of linearly independent number of row vectors or the column vectors. Then we are going to call this as the rank of a matrix. Null matrix has rank 0 and all other matrices has rank at least 1. See, null matrix means every element is 0. So definitely we can say the rank itself is equal to 0 because there is no vector. But if you take any other matrix except null matrix, if you take any other matrix, then definitely rank will be at least equal to 1 but not 0. So only for null matrix the rank is 0, but if you take any other matrix other than null matrix, definitely the rank at least minimum value will be equal to 1 but not 0. And always these are the two important formulas, which is rank of A into B always less than or equal to rank of A and also less than or equal to rank of B. See, rank of A into B is always less than or equal to rank of A and also it is less than or equal to rank of B. See, whatever the rank you are going to get of a matrix A into B, its rank is always less than or equal to rank of A matrix and also less than or equal to rank of B matrix. So therefore we can say always the rank of matrix A is less than or equal to, see, rank of A into B is less than or equal to rank of A and also less than or equal to rank of B. Suppose there is a matrix A with Aij n cross n. See, always it is a square matrix. See, only for a square matrix only we are going to find the determinant. So therefore, if determinant of that matrix is not equal to 0, see, if determinant of that matrix itself is not equal to 0 means all the vectors or all the row vectors or column vectors are independent of each other. See, determinant is not equal to 0 indicates that all the row vectors or column vectors are independent of each other. That is the reason we can say that the determinant of the matrix is not equal to 0. See, if all are independent, we can say the rank itself is equal to the number of rows or number of columns. So therefore, the rank of that matrix will be equal to n because all are independent of each other. So therefore, is equal to n means all vectors are independent of each other. So simply, whenever determinant of that matrix is not equal to 0 indicates that each and every vector is independent of each other. So therefore, we can say the rank of that matrix itself is equal to order of that matrix, which is n. If suppose the determinant of that matrix is equal to 0, suppose if the determinant of that matrix is equal to 0, then what is going to happen? It indicates that some of the row vectors or column vectors are depending upon some of the independent vectors. Means some dependent vectors are going to present. So therefore we can say definitely the rank will be less than n. So therefore we can say this matrix is going to this matrix is going to have some dependent vectors. So therefore if the determinant of the matrix is equal to 0, it indicates that the rank of the matrix will be less than n, means some vectors are linearly depending and some other are independent vectors, means some vectors will be depending upon the independent vectors. So therefore we can say if that matrix determinant is not equal to 0 means all are independent of each other. If all are independent of each other means the rank of matrix itself is equal to order of the matrix. But if it is equal to 0 means some are going to dependent. So therefore the rank of matrix will be always less than n. I have already told you, no matter whether you do the transpose or whether you go for the rank or determinant, see, the determinant of A is equal to determinant of A transpose. Similarly, the rank, see, just by doing interchanging of rows or columns, the nature is not going to get changed. So therefore we can say the rank of matrix A is equal to the rank of A transpose matrix. See, the two elementary transformations does not change the rank of the matrix. I have already told you. See, the first transformation is interchanging either two rows or two columns, and the second transformation is just you are going to replace the ith row or jth column with addition of that row and also by doing addition with respect to other rows. Then definitely that these two transformations are not going to change the rank of the matrix. But if you want to know about the determinant, then definitely the first transformation is going to change the determinant of a matrix, but not the second transformation. So therefore, but in case of rank, no matter whether you go for the first or second, definitely the rank is not going to get changed. So now I'll tell you about some of the important concepts of vectors. Suppose there is a vector V. See, vector V is nothing but it is a combination of the elements. So suppose there is a vector V of combining of elements a1, e2, up to en. So now I want to find what is the determinant of this vector. So determinant of this vector is equal to under root over a1 square plus a2 square up to an square. Suppose I am going to take the two vectors. See, vector v1 is nothing but it is going to comprise of a1, a2, up to an, and the vector v2 is going to combine the elements which is from b1, b2 up to bn. Suppose if you want to do the addition of two vectors means you have to go for the addition of the corresponding elements which is a1 plus b1, a2 plus b2, up to an plus bn. Suppose if you are going to go for the multiplication, or we can say v1 into v2, so these are called a dot product, or simply we can say dot product. Simply v1 into v2 is nothing but it's a dot product of the two vectors. Means simply you have to go for the multiplication of the corresponding elements, which is a1 into b1 plus a2 into b2 plus a3 into b3 up to a into bn. But you have to go for the addition. So therefore, suppose if there are two vectors v1 and v2, and if you want to do the multiplication of the two vectors, then you have to multiply the corresponding elements and overall you have to go for the addition. So a1 into b1 plus a2 into b2 plus a3 into b3 up to plus an into bn. See, if this dot product is equal to 0, then we can say these two vectors are orthogonal vectors. See, if the dot product of these two vectors is equal to 0, then we can say these two vectors are said to be orthogonal vectors. Suppose if this is not equal to 0, then we are going to say these are the non-orthogonal vectors. Means if the dot product is equal to 0 means the angle between these two vectors is 90 degrees. So therefore we can say these vectors are the orthogonal vectors. But if it is not equal to 0 means it is not equal to 90 means there must be some acute angle. So therefore we can say these are the non-orthogonal vectors. Suppose there is an orthogonal vector set. See, suppose there is a matrix V. Suppose there is a matrix V, it is going to combine, it is going to take, see, it's a matrix V, it is going to take all the each and every orthogonal vectors. Suppose V1, V2, V3 up to Vk are the orthogonal vector set. Let me assume these are the some column vectors. So these vectors are going to be orthogonal to each other. So I am going to combine all these things in a given matrix which is V. Then we can say if V1, V2, V3 up to Vk are orthogonal, so therefore no matter whether you do V1 or V2, if you take any two matrix elements and if you do the dot product, definitely it will be equal to 0 because these are the orthogonal vectors. So therefore Vi into Vj is equal to 0 when I is not equal to j. Means there are different vectors, but if you do the dot product of the two similar vectors, it is equal to the determinant of that matrix whole square, of that vector whole square. So Vi dot Vi is equal to modulus of Vi whole square, means modulus of Vi whole square. I is equal to j. Suppose orthonormal vector set. See, orthonormal vector set means it is a special case. It is a special case of a orthogonal vector set. So same thing here. V1, V2, V3 up to Vk are the orthogonal vectors. Let me assume column vectors. See, all these I am going to combine in a matrix V. Suppose orthonormal vector set means if you take any two different vectors and if you do the dot product, definitely it will be equal to 0 because these are also orthogonal vectors. So Vi dot Vj is equal to 0 when I is not equal to j. But if you take the same similar vectors, then definitely you are going to get Vi into Vi is nothing but modulus of Vi whole square, which is equal to 1. Means that you are going to give a length of 1. Means that matrix, or we can say each and every, means we can say simply each and every vector which is going to present in this oral matrix has a length of 1. Means the determinant of, or we can say the modulus of each and every vector present in this orthonormal vector set, length will be always equal to 1. But this is not the case for these things. They may have different lengths. It is not at all necessary. But here always the length of each and every vector will be always equal to 1. But that is not a case for this one. That is the only difference between this orthogonal vector set and the orthonormal vector set. So for orthogonal vector set, whatever the vectors you are going to take, for each and everything, definitely their length will be equal to 1. And linear combination of vectors. See, linear combination of vectors means simply, suppose there is a set combines of V1, V2 up to Vk. So linear combination of vectors means if you want to get a new vector with the combination of the vectors you have, see, we have a set which is V1, V2, V3 up to Vk. But I want a vector which is going to depend on all these vectors. So therefore what I am going to get, I am going to get a new vector which is combination of all these vectors. So therefore A1 into V1 plus A2 into V2 up to AK into Vk. See, A1, A2, AK are nothing but real numbers. Whether it can be positive, it can be negative, it can be fraction, it can be anything. So therefore we can say A1, A2 up to AK are the real numbers. So therefore we can say if you have a vector set of V1 to up to V2 up to Vk, if you want a new vector, then you have to go for the linear combination. Means you have to take these combinations, whatever the things you have, just you have to multiply by A1, A2, A3. Then you can get by using the A1, A2 can be any real numbers. Say linear independence. See, now I will tell you what is the meaning of a linear independence. Linear independence means suppose there is a set. This set V1, V2, V3 up to Vk are independent. Suppose if these vectors are independent. See, let me see in the question they are given a set. They are asking whether this set is independent or dependent. See, suppose independent means this each and every vector should be independent of each other. So suppose there is a A1 into V1 plus A2 into V2 up to AK into Vk is equal to 0. See, now what you are going to do is just you have to do like this. A linear combination of each and every vector which is going to present should be equal to 0. Then what is the condition? If you want to get a null vector, then what are the values should be? A1, A2, A3 should be always equal to. Suppose if you got A1 is equal to A2 is equal to AK is equal to 0, then we can say these vectors, whatever the vectors you are going to present inside in this set are said to be linearly independent. Even if any one A1, A2 or any one if the coefficient is not equal to 0, then we can say the set is going to contain some dependent vectors also. So therefore we can see clearly a1 into v1 plus a2 into v2 up to an k into ak is equal to 0. If you want to get a null vector, then definitely all these coefficients value should be equal to 0. Then only we can say simply, then only this set contains the linear independence, means each and every matrix is a, or each and every vector is a independent, otherwise they are going to get dependent. Or simply we can say determinant is not equal to 0, all are independent vectors, means if you take all these vectors in a matrix and if you find the determinant of that matrix, if you got the determinant value which is not equal to 0, means each and every vector is an independent value, so therefore we can say all are independent vectors. So linearly dependent. See, linearly dependent means suppose there is a set v1, v2 up to vk. See, now I want to find whether if any one vector is going to depend upon the remaining vectors or not. How we are going to get figured out. Same thing now we are going to do the same as we did for the linear independence. Then a1 into v1 plus a2 into v2 up to ak into vk is equal to 0. See, if you want to get null vector, here at least one of these will be not equal to 0. If at least one of these coefficients is not equal to 0, then definitely we are going to say that these vectors are linearly dependent, means some are going to depend upon the remaining thing. Or we can say if you consider all these vectors in a given matrix and if you find the determinant of that matrix, definitely, because if you got the determinant is equal to 0, then definitely we can say some vectors are going to depend upon the remaining one. So therefore some are dependent vectors. See, if each and every coefficient value is equal to 0, then definitely we can say these are the linearly independent vectors. The set is going to contain all the linearly independent. But if at least any of one of the coefficient is not equal to 0, then definitely we can say this is nothing but it is a dependent vectors, means that is going to have the dependent vectors, means some are going to depend upon the remaining thing. So now we'll discuss about the basis of vector space. Basis of vector space means the set of linearly independent vectors which can span all the vectors of vector space are known as the base of the vector space. See, the set of linearly independent vectors which can span all the vectors of vector space are said to be are known as the basis of the vector space. See, it indicates that suppose if you are going to have a set, this set is going to have some linearly independent, means the set must have the linearly independent, means one cannot be represented in terms of the other one. With this combination, you can create any other vector in that span. So therefore, we can say these are called as a base of the vector space. Means these are very much important because with the help of these vectors only we can figure out the remaining vectors in a space. So that is the reason we are going to call this as the basis of the vector space, or we can say these are the very much important vectors. With the help of these vectors only we are going to figure out the remaining vectors in that space. So therefore, the set of linearly independent vectors which can span all the vectors of vector space are known as the basis of the vector space. Dimension. The number of vectors in the basis set is known as a dimension. See, dimension means how many numbers of vectors, how many number of independent vectors which are going to present in the basis. Means basis itself indicates that it is the independent vectors. So the number of vectors which are going to present in the basis set are called as the dimension. So the number of vectors in the basis set is known as the dimension. Subspace. See, if S is a subspace of vector space V, if V1, V2 belongs to S, then V1 plus V2 should be belongs to S, and also A into V1 should belong to S, and also B into V2 should belong to S, and A comma B belongs to the real numbers. Suppose there is a vector space V. So in that vector space, S is called as a subspace when S is called as subspace of a vector space. What are the conditions? See, for a vector space, if you are going to take a small subspace, then what is the condition for that subspace to be called? Suppose if you take any two vectors in that subspace, then definitely their addition should be belongs to same category. See, their addition should be also belong to that subspace, and also A into V1, no matter whatever the A, this should be always lies in the subspace itself, and similarly B into V2, this is also should lie in the subspace. If these conditions are satisfied, then we can say this is a valid subspace, otherwise this is an invalid subspace. So we can say H is a subspace of vector space only when if you take any two vectors in the subspace and if you do the addition of that vectors, then the resultant should be lie in the vector space in the subspace, and also A into V1 should also lie in the subspace, and B into V1, V2 should also lie in that subspace where A comma B are the real numbers. So no matter whatever the coefficient values, their value should be always lies in that subspace. If these conditions are satisfied, then we can say this is the valid subspace of a vector space. So now we'll discuss about the system of the linear equations. So now we are going to see what are the ways of going to get the solutions of a linear equations. So system of linear equations. Suppose Ax is equal to B. Ax is equal to B, it is called as a non-homogeneous because B is not equal to 0. If the, see, Ax is equal to B, where A is a matrix and X is also a matrix and B is also a matrix, where X is a column matrix. See, for this matrix, if B matrix is equal to 0, then we say it is a homogeneous, otherwise it is a non-homogeneous. Means this matrix B is not going to contain 0, non-zero elements are going to present. So therefore we are going to call it as a non-homogeneous. See, the matrix A is going to contain some coefficients which are the A11, A12 up to, so like this we are going to get M cross N. M rows and N columns we are going to get. And X is nothing but here we are going to get the values x1, x2 up to xn, which is N cross N. So if you do the multiplication of these two vectors, then definitely you are going to get M cross 1 because the columns of A should be equal to the rows of X. Then definitely you are going to get the matrix which is M cross 1. So therefore these are the coefficients which are present in this matrix B. So now I want to know whether the solutions exist for this matrix or we can for these equations or not, we are going to figure out. If they exist, whether they are unique solutions or the multiple solutions. If they not exist, then what is the reason? So all these things now we are going to see. So you can see clearly here there are M equations. There are M equations. Means M rows means there are M equations, but the number of variables are N variables because you can see clearly here N cross 1 means the number of rows are N. So therefore here x1, x2 up to xn, which are the unknown values which we need to figure out. So therefore we can say there are M equations with N unknowns. So now we have M equations with N unknowns. So then based on this we need to figure out whether a solution is going to exist or not. So now we are going to see this one. Suppose consistent means yes, solution is going to get occur. What is the reason? See, consistent means yes, solutions are going to exist for these equations. If the rank of matrix A is equal to rank of augmented matrix of A bar B. So therefore, if you take matrix A and A bar B, if you take A bar B, and if you see clearly if the rank of A is equal to rank of A augmented matrix B, or you can say A bar B is nothing but augmented matrix, then if both having the same rank, then definitely we can say that this is a consistent means yes, solution is going to get exist. Whether the solution is unique solution or many solutions or infinite solutions, now we are going to figure out. See, unique solutions when if rank of A is equal to rank of A cross B, A bar B, when this rank is equal to N. The N is called as the unknowns. So therefore, if the rank is equal to N, which is equal to the number of unknowns, then definitely we can say a unique solution is going to get exist. But if both the ranks are equal, but it is less than N number of unknown variables, then we can say this is nothing but infinite number of solutions are going to get exist. See, if both the ranks are equal, but if it is equal to the number of unknown variables means only unique solution is going to get exist. But if both the ranks are equal, but it is less than number of unknown variables, then definitely we can say infinite number of solutions are going to get exist. Means consistent also we can say other words, which is it means B lies in the vector span of A or B linearly dependent on A. So B linearly dependent on A. See, it indicates that it means B lies in the vector span of A or B is linearly dependent on A. Means simply suppose if you have a consistent means solution is going to get exist. So for a certain X, if you do the scalar, if you do the multiplication of A with respect to this X, definitely you are going to get a B. Means B is going to depend upon the vector A. So if you span the vector, if you span this matrix A, then you are going to get a matrix B for a certain value of X. So therefore we can say it means B lies in the vector span of A or B is linearly dependent upon the A. That is the meaning of a consistent. So therefore if you are going to span the matrix A for a certain value of X, definitely you are going to get a B, or we can say a solution is going to get exist. So therefore consistent means a solution is going to get exist only when the rank of A is equal to the rank of B, but if the rank R is equal to the number of variables, then definitely unique solution. If it is less than number of unknown variables, so therefore then you are going to get a infinite solutions. See, inconsistent means you are not going to get a solution for this equations, means no, you are not going to get a solution. When is that case? When rank of A is not equal to rank of A, augmented matrix B. So therefore we can say if both the ranks are unequal, then definitely we are going to call that as the no solution or inconsistent. Then there definitely you are not going to get a solution. So therefore these equations will not have a solution or inconsistent when both the ranks are unequal. So now we'll discuss for the homogeneous equations. So what is the case for homogeneous equations now? We are going to see. Suppose homogeneous equations means I have already told you B matrix should be always equal to 0. So that is the meaning of homogeneous. So here also we are going to get M equations, and here there is a n unknown variables. So therefore here A is a matrix of m cross n, and this is a n cross 1, and this is a m cross 1. Because if you multiply these two vectors, definitely here the number of columns of matrix A is equal to the number of rows of x. So you are going to get finally m cross n. So therefore we can say this matrix is going to contains of this equation is going. There are totally m equations with n unknown variables. N unknown variables are x1, x2 up to xn. So now here always you are going to get a solution. See, always you are going to get a solution. There is nothing like inconsistent. Definitely, if a system is homogeneous, definitely you are going to get a solution. Definitely you are going to get a solution, whether it can be unique or whether it can be infinite. This we are going to see, but solution will be always going to exist, because here if this is 0, if you take all the variables as 0, then definitely no matter whatever the A, definitely A into 0 is nothing but 0. So B is also equal to 0. So therefore we can say always a solution is going to get exist whenever this is a homogeneous equation. Suppose if rank of A is equal to rank of A cross B. Here always constant means always the rank of A is always equal to the rank of A bar B. But if rank of A is equal to rank of B is equal to n, the number of unknown variables, then only you are going to get a unique solution. But if it is less than n, if it is less than unknown variables, then we are going to call it as the infinite solutions. If it is equal to n, you are going to get a unique solution. If it is less than n, definitely you are going to get a infinite solutions. So this is the case. Always you have to remember, for homogeneous always a solution is going to exist. There is nothing like no solution, because if you keep x is equal to 0, then definitely you are going to get a solution. So therefore we can say always a solution is going to get exist for a homogeneous, but not the case for a non-homogeneous. You may get a solution or you may not get a solution for a non-homogeneous, but for homogeneous definitely you are going to get a solution. Suppose rank of A is equal to R. See, if rank of A is equal to R, see, for this homogeneous only, for this homogeneous case only, if rank of A is equal to R, then the number of linearly independent sets of infinite many solutions are n minus r. It is also called as the nullity. See, remember this point is very much important. See, if rank of A is equal to r, the number of linearly independent sets of infinite many solutions are n minus r, where n is the order of the matrix and r is the rank of the matrix. So that is also called as a nullity. So here nullity is equal to n minus r, where n is the order of the matrix and r is the rank of that matrix. Or simply we can say the number of linearly independent sets of infinite many solutions are. So n minus r, this is nothing but here. Then if rank of A is equal to r, it indicates that n minus r, it indicates that nullity, or the number of linearly independent sets of infinite many solutions are n minus r. It is also called as a nullity. Suppose if rank of A is equal to n, see, if rank of A is equal to n, it indicates that this is the order of the matrix. So therefore we are going to get a unique solution. Unique solution is nothing but 0. So therefore only 0 is the solution. Only 0 is the solution which is going to get exist. See, if rank of A is equal to n indicates the order of the matrix, means you are going to get only one solution, because it is equal to the number of unknown variables. So you must get only unique solution which is itself is equal to 0. Or we can say trivial. Trivial means only 0 solution. If rank of A is equal to r, which is less than n, so I have already told you, which is less than n, if the rank of the matrix is equal to less than number of unknown variables, it indicates that you are going to get infinite solutions. So both 0 and non-zero solutions are going to get exist. Means you can get now finite numbers also in the terms of x. You can get 0 numbers and also some non-zero numbers also you are going to get exist. See, the rank of A is equal to n, it indicates that only 0 solution is going to get exist. The rank of A is not equal to n, means less than n, so therefore definitely you are going to get 0 solution, and also non-zero solutions are also going to get exist for this homogeneous equation. So the nullity means n minus r, where n is the order of the matrix and r is the rank of the matrix. So then it indicates that the number of linearly independent sets of infinite many solutions. The number of linearly independent sets of infinite many solutions means the number of sets you are going to get with the help of these things, this many number of solutions are going to get exist. So the number of linearly independent sets of infinite number of many solutions are called as the element. It's also called as the nullity. Now we'll discuss about the eigenvalue and the eigenvector. See, eigenvalue and eigenvector. So this is very much important, because from this definitely you are going to get a question. See, eigenvalue and eigenvector. Suppose there is a matrix A. Suppose it is a matrix A of Aij n cross n. It is always a square matrix. So now the condition is A into x is equal to lambda into x. See, if you multiply A into x, then you are going to get a new matrix which is called as the lambda into x. Then here x is a column matrix and lambda is a scalar number. So therefore we can say x is called as the eigenvector and lambda is called as the eigenvalue for that eigenvector. So here x is called as the eigenvector and lambda is called as the eigenvalue for that eigenvector. So if Ax is equal to lambda into x, then we are going to get x is called as the eigenvector and lambda is called as the eigenvalue for that eigenvector. So if you want to figure out the what is the way of figure out the eigenvalue and the eigenvector, then definitely here you can Ax minus lambda x is equal to 0. So now you can take x as a vector, you can take common. So therefore you are going to get a minus lambda into I into x is equal to 0. So therefore now you can figure out the determinant of this matrix, which is a minus lambda is equal to 0. Then by this way we can figure out. So we can simply say this is nothing but a homogeneous equation, which is a minus lambda I into x is called as a homogeneous equation. Definitely you are going to get a solution, means the determinant of that matrix must be equal to 0. Then only we can get a solution. So therefore determinant of a minus lambda is equal to 0. So by this way you can figure out the eigenvalues. So with the help of these things, if you can keep in this matrix which is a minus lambda into x is equal to 0, if you know the eigenvalues, substitute here, and if you do the equation to 0, then you can produce or you can get the corresponding eigenvector. So for this eigenvalue, if you keep here and if you do the simplification, finally you can get even the eigenvector for that corresponding eigenvalue also you can figure out. So this gives the eigenvectors. So now we will discuss some of the important properties. With the help of these things, we can easily figure out the eigenvalue for any other, or you can say we will now learn about the properties of the eigenvalue and the eigenvector. See, suppose x is a eigenvector corresponding to lambda. If x is eigenvector corresponding to lambda, then kx is also an eigenvector corresponding to lambda only. See, if x is eigenvector for some lambda, kx is also means scalar value, scalar multiplication of the eigenvector is also an eigenvector for this lambda. So therefore we can say x is a eigenvector, means it is not a unique one. So you can get scalar values also. So therefore if x is an eigenvector corresponding to lambda, then kx is also an eigenvector corresponding to lambda. If x is eigenvector of A, then x can correspond to exactly one eigenvalue of A. So simply suppose here, suppose for a matrix A, suppose n matrix n by n. So for n by n means n eigenvalues you are going to get. So for each an eigenvalue, you are going to get a different eigenvector. So therefore it will be a unique one. For a given eigenvalue, you are going to get a unique eigenvector. Any lambda, there may be one or more linearly independent eigenvectors. For any lambda, there may be one or more linearly independent eigenvectors. So if you take any eigenvalue, you can get one or more linearly independent eigenvectors also you are going to get. If A n cross n matrix, there may be minimum n linearly independent eigenvectors. Means you can say simply for n by n matrix is nothing but you are going to get n eigenvalues. See, for each eigenvalue is nothing but linearly independent of the remaining things. So therefore you can get for each eigenvalue you are going to get some linearly independent eigenvector. Means all eigenvectors whatever you are going to get with the help of eigenvalues, all are said to be linearly independent of each other. Means one is independent of the other one. If all lambda are distinct, then corresponding to these there are exactly n linearly independent eigenvectors. Means if all the eigenvalues of a given matrix are independent of each other, means different, then for each and every lambda you are going to get eigenvector, and if you see all these eigenvectors, these are independent of each other. There is no dependency between these eigenvectors. If not all lambda are distinct, then there may be maximum n linearly independent eigenvectors. Suppose if they are all are not same, means all are different. Suppose if all are not distinct, means all are not same, or we can say if all are not different, then there may be a maximum only you can get n linearly independent eigenvectors. See, if they are different, means definitely you are going to get eigenvectors which are linearly independent. Suppose if they are not different, some are same, then maximum you can get n linearly independent eigenvectors. Eigenvalues of symmetric and Hermitian matrix are always purely real. See, eigenvalues of symmetric means A transpose is equal to A, and Hermitian matrix means A to the power of theta is equal to A. If a matrix satisfying these conditions, then eigenvalues of symmetric and Hermitian matrix are always purely real, but may not be necessarily distinct and positive or negative. See, eigenvalues of symmetric and Hermitian matrix are always purely real, but may not be necessarily distinct and positive or negative. Means it can be anything. See, the eigenvalues of symmetric and Hermitian matrix are always purely real. Means it may not necessarily be always distinct. It can be same, it can be distinct, it can be anything. They can be same, they can be distinct, or they can be positive, or they can be negative. Anything it can happen. Therefore, eigenvalues of symmetric or Hermitian matrix is purely real. They can be same or they may not be same. It's not compulsory. And also they can be positive, they can be negative, it can be anything. Eigenvalues of real skew symmetric and skew Hermitian are purely imaginary or zero. See, I have already told you, skew symmetric matrix means A to the power transpose is equal to minus A, and skew Hermitian means A to the power theta is equal to minus A. If the eigenvalues of the skew symmetric or skew Hermitian are always purely imaginary or zero. So we can get, see, the eigenvalues of skew symmetric and skew Hermitian are always purely imaginary or zero. They can be purely imaginary or zero, but not more than this. See, eigenvalues of orthogonal and unitary matrix are of unique modulus. Means, see, suppose you are going to get, see, for orthogonal matrix I have already told you, where A into A transpose is equal to I, and for unitary matrix which is A into A to the power theta is equal to I. See, for these matrices, the eigenvalues, suppose if you are going to get a complex number, then always their A square plus B square is equal to 1, means their determinant will be always equal to 1. So therefore we can say here the eigenvalues of orthogonal matrix and also unitary matrix, if they are going to get a complex, then definitely their modulus value will be always equal to 1. Suppose for a matrix A, you are going to get some lambda. See, for this matrix A, you are going to get some eigenvalue lambda. So for this eigenvalue, you can figure out the eigenvector x. Suppose for A to the power of k, so for A to the power of k matrix, then eigenvalue will become lambda to the power of k, but still the eigenvector is same. So therefore we can say for A to the power of k, the eigenvalue is changed by lambda to the power of k, but still the eigenvector is same. And also the transpose of the matrix, just by doing the transpose, the eigenvalue and the eigenvector will not change. So therefore we can say here, by doing the transpose, the determinant of the determinant will remain same, the rank will remain same, and also the eigenvalue and the eigenvector will remain same. So these are the very important way of relating the previous concepts. Then you can interrelate each and everything. So for a matrix A, if the eigenvalue is lambda, then eigenvector is x. For A to the power of k, then eigenvalue will become lambda to the power of k, but still the eigenvector will be same. But for A transpose, still the eigenvalue and the eigenvector is same. So now we'll discuss the trace. So now discuss the trace of matrix. So now we'll discuss about the trace of a matrix. See, I've already told you, trace of a matrix is nothing but just you have to add the, you need to add the elements of the diagonal, or simply we can go for the another process, which is if you add all the eigenvalues, it is equal to the trace of the matrix. So therefore, if you add all the eigenvalues, it is equal to the trace of the matrix. And if you do the product of all eigenvalues, then you are going to get the determinant of the matrix A. So simply we can say, if you want to know what is the trace of a matrix, you need to add all the eigenvalues. If you want to know what is the determinant of the matrix, then you have to multiply all the eigenvalues. See, the eigenvalues of A and A transpose are same. Just now we have discussed. See, just by doing the transpose of a matrix, the determinant will not change, the rank will not change, and the eigenvalues and eigenvectors are also not going to get changed. So therefore now see, suppose for a matrix A, if the eigenvalue is lambda, then for k into A, then eigenvalue will become k into lambda. For A inverse, the eigenvalue will become 1 by lambda. For adjoint of A, the eigenvalue will become mod A by lambda, and for A transpose, the eigenvalue will remain same as the eigenvalue of A, which is lambda. So for the matrix A, if the eigenvalue is lambda, for A to the power of k, the eigenvalue will become lambda to the power of k, but still the eigenvector is x. But for k into a, the eigenvalue will become k into lambda. And now for A inverse, the eigenvalue will become 1 by lambda. And for adjoint of A, which is we are going to get the eigenvalue which is mod of A by lambda. For A transpose, still the eigenvalue will be equal to lambda. See, eigenvalues of diagonal and triangular matrix are the diagonal elements. I have already told you, either for the upper triangular matrix or the lower triangular matrix or the diagonal matrix, always the eigenvalues itself are the diagonal elements. So therefore we can say the eigenvalues are the diagonal elements for the triangular matrix, for upper triangle, lower triangle, and also for the diagonal matrix. If determinant of matrix A is equal to 0, means at least one of the eigenvalues is 0. So I have already told you, the determinant of the matrix A is equal to 0, we can see few things which are we can conclude few important concepts, which is some vectors are going to depend upon the remaining vectors, and also I have already told you here the determinant of the matrix is equal to, you have to go for the product of the eigenvalues. It indicates that one of the eigenvalues is 0, then only the product will be equal to 0. Say at least one, it may be more than one, but at least one definitely should be equal to 0. If determinant of the matrix is not equal to 0, it indicates that each and every vector is independent of each other. So therefore we can say all the eigenvalues are non-zero. See, all the eigenvalues are non-zero. Then only we can say here, if all eigenvalues are not equal to 0, their product will be always not equal to 0. So that is the reason the determinant of the matrix is not equal to 0, means all are linearly independent vectors, and also we can say all eigenvalues are non-zero. See, elementary transformation does not change the eigenvalues of the old matrix and the newly formed matrix. See, I have already told you the first elementary transformation will change only the determinant of a matrix, but second elementary transformation doesn't change as the determinant of a matrix. But if you want to know what is the rank by element transformation first and second, the rank will never change. Similarly, by doing the elementary transformations, the eigenvalues of the old matrix and the new matrix are going to remain same. Means the eigenvalues are not going to get changed. If the eigenvalues are not going to get changed, means the eigenvectors are also not going to get changed. Two linearly independent different eigenvectors of symmetric matrix are always orthogonal, which is x1 dot x2 is equal to 0. See, two linearly independent eigenvectors of symmetric matrix are orthogonal. See, I have already told you, for a symmetric matrix means transpose of the matrix is equal to the matrix, then we are going to call it as a symmetric matrix. So for a symmetric matrix, always the eigenvalues are purely real. So for each and every eigenvalue, if you got a eigenvector, these are the linearly independent, means they are orthogonal to each other. See, linearly independent is nothing but there are independent means they are orthogonal to each other. So x1 dot x2 is equal to 0. Now we are going to discuss about the Cayley-Hamilton theorem. See, this is a very much important theorem. Suppose there is a matrix here. It is going to have a square matrix which is Aij n cross n. So now here I want to find what is the characteristic equation, which is the characteristic equation we can even say which is the determinant of the A minus lambda I is equal to 0. So if you do the determinant of A minus lambda is equal to 0, then you are going to get a equation in terms of lambda. The lambda is called as the eigenvalue. Suppose the equation is a n lambda power of n plus a n minus 1 lambda power of n minus 1 up to a naught is equal to 0. So let me assume this is the f of lambda. Because it's a function of lambda, I am going to assume it is the f of lambda. It is also called as the characteristic equation. So now what I am going to do is here, in place of lambda, I am going to replace the matrix A. So in place of lambda, I am going to replace the matrix A, because this matrix A is going to satisfy its own characteristic equation. So therefore, in place of lambda, substitute here matrix A. So A and lambda a to the power of n up to here. But if you see here, A1 into lambda means A1 into A. But here A naught is a scalar. But you are going to write in terms of matrices. So A naught into I is equal. Here 0 is called just a number, but here 0 is a vector. Or you can say 0 is a matrix, column matrix. So definitely you can see it's just a matrix, 0 null matrix. So therefore we can say here, this the Cayley-Hamilton theorem is going to tell you that matrix is going to satisfy its own characteristic equation. That is the beautiness of the Cayley-Hamilton theorem. See, the matrix is going to satisfy its own characteristic equation. So therefore we can say simply here, this 0 is called as a null matrix. So this is used to calculate the inverse and higher powers of A. See, now you don't have to do A square, A cube, A4 in a very high amount of consecutive manner. So you don't have to do you don't have to invest huge amount of time to calculate the a square a cube a4. But now you can easily figure out within a very fraction of seconds if you use this theorem, which is the Cayley-Hamilton theorem, means the matrix is going to satisfy its own characteristic equation. So with the help of this, we can usually calculate the inverse and higher powers of any matrix. Calculating any function of matrix here. Suppose they are given f of a, some function they have given. Calculating any function of matrix here. Suppose they have given a f of a, they have given some function. So now here I want to find what is the characteristic equation of matrix here. Now I want to figure out what is the characteristic equation of the matrix A I want to figure. Then what I am going to do, which is determinant of A minus lambda is equal to 0. So then I am going to get a certain equation. That equation I am going to assume it is d of lambda. So d of lambda I am going to assume. Then this is called as a d of lambda. But here already there is an equation which is by using the polynomials, which is f of lambda is equal to d of lambda into q of lambda plus r of lambda. Where d is called as the d, when here f is called as the f of lambda is equal to d of lambda into q of lambda plus r of x. Where r of x is called as the remainder, q is called as the coefficient, and d is called the divisor, and this is called as the dividend. So therefore we can say f of lambda is equal to d of lambda into q of lambda plus r of lambda. But here always this the remainder lambda coefficient value, the power should be always lesser than the remainder of d of lambda. So therefore we can say the remainder power of, see always the power of r of lambda should be always less than the power of d of lambda. See always r of lambda will have a lesser power when compared to d of lambda. So d of lambda. But here if you are going to write in terms of a, so if you write in terms of a, means every time this suppose if you are going to replace here a, then here also you have to replace by a, but d of a is nothing but the characteristic equation of matrix A, it is equal to 0. So definitely this also equal to 0. So 0 and everything is again 0, then f of a is equal to r of a. So if you know r of lambda, in place of lambda substitute a, then you can get any high. If you get if you are given any function of lambda, you can get this huge expression to a very small one, which is r of a. Therefore now you can easily figure out the r of a. See the power of r of x. Suppose if it is a 2, suppose d of lambda has a power 2, means it has to be 1. So therefore we can say a lambda plus 1. If d of lambda has a power 3, then it can be 2, which is lambda minus a into lambda minus b. Suppose if it is of 4, then definitely it has to be 3. So lambda minus a into lambda minus b into lambda minus c. So simply thing is, suppose in the question they are going to give some function f of a. The first thing is we have to find what is the characteristic equation of the a. So let me assume d of lambda. Then what you are going to do is it is equal to 0. Then f of lambda is equal to d of lambda into q of lambda plus r of lambda. See in place of lambda, if you are going to substitute a, then definitely this value will become 0, because the characteristic equation is going to satisfy its own. The matrix is going to satisfy its own characteristic equation. This is equal to 0. So this value will become 0. So I think you are going to get is f of a is equal to r of a. So this is the only thing that you are going to get. So if you know what is the value of r of lambda, just substitute in place of lambda a, then you are going to get f of a is equal to r of a. Means f of a is a very complex function of a, but still you are going to get r of a is a very simple function of a. It's a very easy thing you are going to get. See always the power of r of lambda will be always lesser than the power of d of lambda. That is the beautiness. If you want 1 power means a lambda plus b. If you want 2 powers means lambda minus a into lambda minus b. If you want 3 power 3, which is lambda minus a into lambda minus b into lambda minus c. I will tell you about the diagonalization of a matrix. Diagonalization of a matrix. Suppose there is a matrix A. See for this matrix, you have figured out the eigenvalues with the help of determinant of a minus lambda is equal to 0. So with the help of these things, you have got the eigenvalues, which is lambda 1, lambda 2 up to lambda n. So for each and every eigenvalue corresponding also, you are going to get the eigenvector x1, x2 up to xn. Then what I am going to do is I am going to take a diagonal matrix which are going to contain all the eigenvalues. See all the eigenvalues I am going to take in terms of the diagonal. So the remaining elements are always, the non-diagonal elements are always 0. Now I am going to take another matrix P. See for lambda 1, the eigenvector is x1. For lambda 2, the eigenvector is x2. And for lambda n, the eigenvector is xn. So these are the column vectors. So for each and every column, I am going to keep all these things here. Now, see, I know the value of D, I know the value of P. Can I relate D, P and A? Can I relate anything like this one? Then definitely you are going to get, see here, D is equal to pop. or we can say simply d is equal to pop, and you have to go for the first one as the -1. So therefore, if you want d to the power of n means only here you have to go for the a to the power of n, you need to go. And similarly, if you want a, see if you want a, then you have to go for the PD P inverse, or if you want a to the power of n means P d to the power of n p to the power of -1. So therefore, see, this is a very important relation. So therefore, always d is equal to pop. So therefore, d is equal to pop means p to the power of inverse a pop. If you want d to the power of n means p to the power of -1 into a to the power of n into p. But if you want a, then what you have to do? The first thing is here p you need to take p d, again then you have to go for the p inverse. If you want a to the power of n, p into d to the power of n into p to the power of -1. See, in this way now you can relate a in terms of the pd, you can relate p a in terms of pd, yes or no? So therefore, here we can represent a in terms of the p matrix and also p matrix. So always remember one thing, here d is equal to pop. So d is equal to pop means nothing but p inverse ap. If you want d to the power of n means p to the power of -1 into a to the power of n p. If you want a means, if you want a, first thing is here you have to multiply by p, then here p inverse. So p inverse, if you want a to the power of n means p into d to the power of n into p to the power of -1. So this is called as the diagonalization of a matrix. Means you can represent matrix A in terms of PD, which is P is called as the, it is going to contain all the eigenvectors, and D is called as the diagonal matrix. It is going to contain all the eigenvalues in the terms of the diagonal. Now we are going to learn about some of the important points which are going to discuss in the linear algebra. The first one is that you can see clearly here the principal diagonal. The principal diagonal in a square matrix contains all the diagonal elements. This point I have already told you that if you take any square matrix, there is a principal diagonal. So in the principal diagonal, it is going to contain all the elements. So these elements we are going to call it as the diagonal elements. And the second point is sum of two diagonal matrix is a diagonal matrix. Yes, if you take the sum of two diagonal matrix, the final output also we are going to get the diagonal matrix. And I have also told you the different types of operations that we are going to do on the diagonal matrix. All those properties also we have discussed. And the product of two diagonal matrices is also a diagonal matrix. So you can say clearly that if you do the addition of two diagonal matrix, still you are going to get the diagonal matrix. I have already told you the product of two diagonal matrix is still a diagonal matrix. So we can say clearly the sum of two diagonal matrix is a diagonal matrix, and the product of two diagonal matrix is also a diagonal matrix. And the third important property is identity property, which is if you do the multiplication of identity matrix with any other non-zero matrix, then we are going to get that non-zero matrix itself, which is a into I is equal to I into a is equal to a. And also I have told you that the sum of two lower triangular matrix is also a lower triangular matrix, and sum of two upper triangular matrix is a upper triangular matrix. Means if you do the addition of two lower triangular matrix, still the output will be lower triangular matrix, and the sum of two upper triangular matrix, still you are going to get the upper triangular matrix. And the product of two lower triangular matrix is again a lower triangular matrix, and the product of two upper triangular matrix is a upper triangular matrix. Means we can say if you do the addition of two lower triangular matrix, the output will be a lower triangular matrix, and if you do the product of two lower triangular matrix, then the output is still a lower triangular matrix. Similarly, if you do the summation of two upper triangular matrix, you are going to get the net output as a upper triangular matrix, and also the product of two upper triangular matrix is also a upper triangular matrix. So these are some of the important properties of upper triangular matrix and the lower triangular matrix. And I have already told you the definition of the upper triangular matrix and the lower triangular matrix. Upper triangular matrix means the downward portion of the principal diagonal elements are completely zero, whereas for a lower triangular matrix, we can say clearly the data above the upper triangular matrix are completely zero. This is the basic difference between a lower triangular matrix and the upper triangular matrix, and I have already told you the eigenvalues of the upper triangular matrix, lower triangular matrix and diagonal matrix are the diagonal elements itself. So if you want to figure out the determinant of any upper triangular matrix, lower triangular matrix or diagonal matrix, just you have to do the multiplication of the eigenvalues, which is the multiplication of the diagonal elements. So therefore this you are going to get directly the determinant of any matrix. Now the next point is the number of different elements we can put in a symmetric matrix of order n. See how many different elements we can keep, how many number of different elements we can keep in a symmetric matrix of order n. So if you can see clearly, in the first row we can keep n elements, In the second row we can keep n minus 1 elements. In the third row we can keep n minus 3, n minus 2 elements, and if you go on up to n, finally you are going to get a 1 element. So if you add all these things, n plus n minus 1 plus n minus 2 up to 1, it is nothing but 1 plus 2 plus up to n minus n. So therefore finally you are going to get summation of n digits is equal to n into n plus 1 by 2, or we can say sum of consecutive n digits is equal to n into n plus 1 by 2. So these may number of different digits or unique elements we can keep in a symmetric matrix of order n. And also the important property, which is a into a to the power of minus 1, or we can say a, the product of matrix and its inverse. Whether you do in any manner, still the output will be always an identity matrix, which is a into a inverse is equal to a inverse into a is equal to I, whereas inverse of a matrix is going to exist only when the determinant of that matrix is non-zero. Otherwise the inverse is not going to exist for any square matrix. Suppose in the question they are given a matrix which is a square matrix. Suppose let me assume a is equal to aij of order n cross n. So now I want to know what is the symmetric and skew symmetric, what is there present in this matrix I want to figure out. So you can take any random matrix, you can write that matrix as a summation of the symmetric matrix and also the skew symmetric matrix. So if you take any random matrix, you can make addition, means you can figure out matrix A with the help of two things, which is addition of the symmetric matrix and also the skew symmetric matrix. So therefore symmetric matrix will be the formula of the symmetric matrix, which is half of A plus A transpose, whereas skew symmetric matrix we are going to get half of A minus A transpose. So if you want to know what is a symmetric matrix from this random matrix, just we have to do this operation, which is half of A plus A transpose. Like this you are going to get the symmetric matrix, and if you want to figure out the skew symmetric matrix, just we have to do the half of A minus A transpose. Then you can easily get the skew matrix and also the skew symmetric matrix and also the symmetric matrix from a random matrix. Suppose there is a matrix A which is a square matrix of Aij bracket with n cross n order. So now I want to know what is the adjoint of the matrix A. See, adjoint of the matrix A is nothing but, it is nothing but cofactor of the matrix A. Now you have to do the transpose of this one. Means first you have to find what is the cofactor of the matrix A, and then you have to do the transpose. Then you are going to get the adjoint of the matrix A. Now what is the meaning of the A inverse? A inverse is called as it is equal to adjoint of A by determinant of A. So therefore you can see clearly, if you want to figure out the A inverse, it is equal to adjoint of A by A inverse, or you can say A inverse is equal to adjoint of A by determinant of A. So whenever the determinant of matrix is not equal to 0, then only the inverse of the matrix is going to get exist. Otherwise we can say if determinant is equal to 0, then inverse of any square matrix is not going to get exist. So simply we can say A inverse is equal to adjoint of A by determinant of A, and adjoint of A is equal to cofactor of A over the power of transpose. So in this way we can figure out the inverse of matrix of any square matrix. Suppose there is a 2 by 2 matrix. Let me assume which is the matrix is equal to A, B, C, D. Then what is the A inverse? So A inverse is equal to, the direct shortcut formula for this one is A inverse is equal to 1 by AD minus BC into D minus B minus C A. So this is a very easy way to remember. If you know this one, you can easily solve any question every fraction of second. So therefore A inverse is equal to 1 by AD minus BC into D minus B minus C A. And if you want to know what is the inverse of an identity matrix, it is still equal to identity matrix. So if you do the inverse of any identity matrix, still it is equal to identity matrix itself. See, I have already told you, zero solution is also called as a trivial solution. See, zero solution is also called as a trivial solution, means trivial means it is a zero solution, and non-zero solution is also called as a non-trivial solution. See, in the examples or in the questions, they are going to give you that they are going to give some equations, and they are going to ask you whether these equations has trivial solutions or non-trivial solutions. Means trivial means for these equations zero solution is going to get exist. Non-zero means non-zero is also called as a non-trivial. So therefore we can clearly indicate that zero solution is also called as a trivial solution, whereas the non-zero solution is also called as the non-trivial solution. See, trivial solution won't exist for non-homogeneous equation. This point I have already told you, because non-homogeneous means where Ax is equal to B, if whenever the matrix D is non-zero, then we are going to call it as a non-homogeneous. So no matter whatever the value of X, if you are going to take the X values as 0, then definitely LHS is not equal to RHS. So therefore we can say clearly that trivial solutions are not going to exist for the non-homogeneous equations, because always trivial solutions means it is a zero. So zero cannot be a solution for a non-homogeneous equation, but zero solution is always a solution for a homogeneous equation. So now dimension, what is the meaning of a dimension? I have already told you a dimension means the number of independent vectors in a basis vector set, that is called as the dimension. Or we can even say that number of linearly independent vectors in a matrix, or we can also call as the rank of the matrix. So dimension means, suppose in a matrix I want to know how many number of independent vectors. So the number of linearly independent vectors in a matrix is called as the dimension, or we can even call as the rank of a matrix. See, the number of independent vectors, whether it can be row vectors or the column vectors, always it will be same. So now in the question, if they are asking about the dimension of the null space, the dimension of null space means how many number of dependent vectors are present in a matrix, or simply we can say total number of vectors in the matrix minus rank of matrix, or we can even say which is number of total vectors in the matrix minus dimension of the matrix, or we can say the number of linearly independent vectors, which is nothing but rank of a matrix. So therefore the dimension of null space is nothing but it indicates that how many number of dependent vectors in a given matrix, which is total number of vectors minus rank of a matrix. Eigenvectors are non-zero vectors. See, eigenvectors are always non-zero vectors, means there is nothing like always zero. Say eigenvectors cannot be a null vectors, so therefore definitely it should be a non-zero vectors. See, for triangular matrix, eigenvalues are the diagonal elements. I have already told you this point. For a triangular matrix, whether it is upper triangular matrix or the lower triangular matrix, or for even diagonal matrices, always the diagonal elements are itself the eigenvalues. Suppose for orthogonal matrix, if lambda is the eigenvalue of A, for orthogonal matrix, if lambda is the eigenvalue of A, then 1 by lambda is also an eigenvalue of A. So I have already told you the orthogonal matrix. If any matrix satisfying the condition which is A into A transpose is equal to I, then we are going to say that matrix is said to be a orthogonal matrix. Means we can say A inverse is equal to A transpose. So therefore, if lambda is the eigenvalue of A, then definitely 1 by lambda is also an eigenvalue of A, because I have already told you the determinant, or we can say the determinant or the determinant of that orthogonal matrix must be equal to 1. So therefore, this is only possible if 1 is lambda, then the other has to be 1 by lambda, then only the determinant or the product will be equal to 1. For a symmetric square matrix, the eigenvalues are always real. See, I have already told you, for a symmetric square matrix, the eigenvalues are always real, may not be a distinct always, that it can be positive or negative. See, I have already told you for a symmetric matrix, for a symmetric matrix and also for Hermitian matrix, always the eigenvalues are always real. It may be positive, it may be negative, they may be same, they may be distinct, or we can say they may be different. It is not at all necessary, they have to be always equal. So therefore we can say for a symmetric square matrix or the Hermitian matrix, always the eigenvalues are always purely real, means they can be either positive, they can be negative, they can be same, they can be even different. But for a skew symmetric matrix and also for the non-Hermitian matrix, definitely the eigenvalues are purely zero, or we can even say, or there may be purely imaginary. And rank of A is equal to rank of A transpose. I have already told you this point is very much similar, which is the determinant of the A and also the determinant of the A transpose is same, and also rank of matrix A is equal to rank of A transpose matrix, and also the eigenvalues of A and A transpose is same, and determinant of A and transpose is also same. Means by doing the transpose of a matrix, the rank will remain same and the determinant will remain same, and the eigenvalues and the eigenvectors are also going to remain the same. Elementary transformation does not change the eigenvalues of the matrix and newly found matrix. So therefore, I have already told you there are two transformations. Only by first transformation the determinant is going to get changed, but not by the second transformation, whereas the rank of a matrix is not going to get changed by either of these two transformations, or we can even say the eigenvalues are also not going to change if you do the transformation of any elementary transformation. Only determinant is going to change only by the first transformation, and remaining everything is going to remain no matter what the transformation you are going to do. Suppose there is the number of multiplications present in a matrix of P of m cross n into Q of n cross r is. See, now I want to know how many number of multiplications are going to present if you want to do the multiplication of two matrices, matrix P of order n cross n and the matrix Q of order n cross r. See how many number of multiplications are going to present if you want to do the multiplication of two matrices P of n cross n and Q of n cross r, which is nothing but m into n into r. So it is equal to m into n into r. These were the number of multiplications which you are going to do if you want to do the product of two matrices of order m cross n and n cross r, which is equal to m into n into r. Suppose there is a coordinate system. So let me assume it's a two coordinate system. There are 3 points. So with the help of these 3 points, we can figure out a triangle, or we can say we can get a triangle with the help of these three vertices, which is x1 comma y1 and x2 comma y2 and the x3 comma y3. Then what is the area of this triangle? So if you want to know what is the area of the triangle, which is half of determinant, or we can say modulus, because area will be always positive, so you have to go for the modulus of the x1 into y2 minus y3 plus x2 into y3 minus y2 y1 plus x3 into y1 minus y2. So you can see clearly, which is half of x1 into y2 minus y3, and the next is 2 3 1 and the next is 3 1 2. Just you have to go in that process. So therefore the area of a triangle is equal to half of determinant of x1 into y2 minus y3, and then you have to go for the 2 3 1 and next is 3 1 2. So if you go this process, definitely you are going to get the area of the triangle, and area of the triangle will be always positive. So that is the reason you have to take a modulus sign here. So therefore area of a triangle is equal to half into modulus of x1 into y2 minus y3, and then you have to go for the 2 3 1 and then 3 1 2. See now, if A is upper triangular matrix, then the eigenvalues of A are the diagonal elements of it. See, I have already told you, if a matrix is either upper triangular matrix or the lower triangular matrix, then definitely the eigenvalues are the diagonal elements of that matrix itself. So therefore, if A is a real symmetry, then eigenvalues of A are always real. It can be either positive, negative, and may not be always a necessarily distinct. So therefore, we can say if a matrix is a symmetric matrix, or even we can say Hermitian matrix, definitely the eigenvalues are always purely real. They may be positive, they may be negative, they may be same, or they may be even distinct. And also, if A is a real, then eigenvalues of A and A transpose is same. I have already told you the rank of matrix A and the rank of A transpose matrix A is same, and also determinant of the matrix A and also determinant of A transpose matrix are also same, and also the eigenvalues and the eigenvectors of A and A transpose matrix are also still the same. If all the principal minors of A are positive, then all the eigenvalues of A are also positive. So this is a very much important statement. If all the principal minors of A are positive, then all the eigenvalues of A are also positive. See, if you take the principal minors of matrix A are positive, means if all are positive, it definitely indicates that the determinant is also positive. So therefore we can say the eigenvalues are also positive. So whenever the principal minors of the matrix A are always positive, it indicates that the eigenvalues of that matrix are also always positive. See, eigenvalues of identity matrix is 1, because for identity matrix only the diagonal elements are 1. So therefore for a diagonal matrix or any identity matrix, or we can say even for a upper triangular matrix or lower triangular matrix, diagonal elements itself the eigenvalue. So therefore diagonal elements are 1. So therefore we can say the eigenvalues of the identity matrix are 1. A is equal to B, then eigenvalues of A is same as the eigenvalues of B. Suppose if two matrices are equal, it indicates that if any two matrices are same, means the corresponding elements are also same. If the corresponding elements are same, it indicates that if eigenvalues of matrix A and the eigenvalues of the matrix B are same. If eigenvalues are same, it indicates that the eigenvectors are also same. If you want to know what is the determinant of A transpose into A inverse, so if you in the question if they are asking what is the determinant of A transpose into A inverse, say I have already told you determinant of A into B is equal to determinant of A into determinant of B. So by using that property, we can figure out like this: the determinant of A transpose into determinant of A inverse. But determinant of A transpose is equal to determinant of A matrix, but determinant of A inverse is equal to 1 by determinant of A. So these both are going to get cancelled, and finally you are going to get the 1. So therefore we can say clearly the determinant of A transpose into A inverse is equal to 1. Suppose here if determinant of modulus A, or we can say if determinant of matrix A is not equal to 0, then Ax is equal to B can be written as x is equal to A inverse into B. It leads to a unique solution. Suppose there is a linear equations, let Ax is equal to B. Suppose the determinant of the matrix is not equal to 0, then we can get x is equal to A inverse into B, because if you multiply A inverse on LHS and RHS, you are going to get x is equal to A inverse into B. So now, with the help of this multiplication of A inverse into B, you are going to get a column matrix, and if you compare these elements, you are going to get the unknown values of x. So this is going to give you a unique solution. If the determinant is not equal to 0, then all the eigenvalues are also non-zero. See, I have already told you, if the determinant of any matrix is not equal to 0, it indicates that all the elements, or we can say all the vectors in the given matrix, are independent of each other. If they are independent of each other, and also I have already told you that the determinant of any matrix is equal to the product of the eigenvalues. If determinant is not equal to 0, it indicates that the eigenvalues are also not equal to 0. If determinant of A is not equal to 0, then all the row vectors or column vectors are independent. Yes, this point I have already told you. If determinant is not equal to 0, it indicates that all the row vectors and the column vectors are independent of each other. Then definitely you are going to get that matrix A determinant is not equal to 0. A is a complex matrix, means containing complex numbers, then eigenvalues are real only if A is equal to a to the power of theta. See, I have already told you, if for a symmetric matrix and also for the Hermitian matrix, the property is the eigenvalues of these are purely real. Purely real means it can be the positive, negative, it may be same or it may be different. See, A is equal to a to the power of theta. This indicates that the matrix is satisfying this condition. It indicates that that matrix is nothing but it is a Hermitian matrix. Then Hermitian matrix itself indicates that it is going to contain some complex numbers. So if any matrix satisfying this property, which is A is equal to a to the power of theta, then we are going to call that matrix as the Hermitian matrix. Definitely for Hermitian matrix, the eigenvalues are purely real. It may be positive, it may be negative, it may be same, or it may be even distinct. Suppose if you want to find what is the rank of A into A transpose, I have already told you rank of A into B is always less than or equal to minimum of rank of A comma rank of B. But rank of A transpose and rank of A both are same. So therefore definitely we can say the rank of A into A transpose is equal to the rank of A. The rank is not going to get changed. And determinant of A plus B is never equal to a determinant of A plus determinant of B. See, this property is not at all equal. So if there is a determinant of A plus B matrix is never equal to determinant of A plus determinant of B. So here, suppose if A is a matrix of order m cross n, if m is equal to n, then we can say this matrix is a square matrix. Then there exists a system which has a solution. If suppose it is a square matrix, then definitely we can say, if there is a square matrix means we can say the number of equations is equal to number of variables. If number of equations is equal to number of variables, definitely we can say a solution is going to get exist. See, always if the number of variables is equal to number of equations, if number of equations is equal to number of variables, then definitely we can say that a solution is going to get exist. Whether the solution is a unique solution or many solution, but definitely you are going to get a solution. So listen carefully. Here Ax is equal to B. I have already told you. See here, suppose A is the order of m cross n and X is the order of n cross 1, then definitely we can say the matrix B is of order of m cross 1. So therefore we can say always if both is a square matrix, if the coefficient A is a square matrix means the number of variables is equal to the number of equations, then definitely you are going to get a solution. Whether a solution is unique solution or whether it can be infinite solutions. Suppose here lambda 1 comma lambda 2 is the eigenvalues of the matrix A. We are going to assume that matrix is a square matrix, or we can say it is a 2 by 2 matrix. Then only we are going to get the two eigenvalues. Then what is the eigenvalues of J A square plus B A plus C I? Then what is the eigenvalues of this matrix we need to figure out, of this overall matrix. See, I have already told you for A square, the eigenvalues will become square of individual, so lambda 1 square and lambda 2 square. But for this matrix A, the eigenvalues are lambda 1 and lambda 2, and for identity matrix, the eigenvalues are 1. So 1 into C is nothing but C. So therefore we can say clearly here, if you do a scalar multiplication for any matrix, the eigenvalues are also going to multiply by scalar quantity. So therefore the overall eigenvalues will become J into lambda 1 square plus B into lambda 1 plus C into 1 is nothing but C. These are the one eigenvalue, The other eigenvalue is a into lambda 2 whole square plus b into lambda 2 plus c. So these are the two eigenvalues we are going to get. So therefore, if lambda 1 and lambda 2 are the eigenvalues for a square plus b plus c is nothing but we are going to get a into lambda 1 square plus b into lambda 1 plus c, and also a into lambda 2 square b into lambda 2 plus c. So these are the eigenvalues we are going to get, because if you do the square, the eigenvalues are also going to get square. If you multiply by a scalar quantity, the eigenvalues are also going to multiply by same scalar quantity. Eigenvectors of a, the eigenvectors of a and a square plus b a plus c I is still same. See, the eigenvalues are going to get changed, but the eigenvectors are still going to remain the same. So therefore, you can see clearly the eigenvalues are going to get changed, but the eigenvectors are going to still remain the same. Suppose there is a 3 by 3 matrix. Suppose there is a 3 by 3 matrix. Means 3 by 3 matrix means the eigenvalues is equal to the number of, you can see the order of the system. So therefore, the eigenvalues of lambda 1, lambda 2 and lambda 3. Then what is the trace of a cube minus 3a square? Then I want to know what is the trace. Trace is nothing but we have to go for the product, or you can say if you want to know trace of a matrix, it is the sum of the eigenvalues. So now I want to know what is the eigenvalues. So for this, the eigenvalues are nothing but, see, for a cube, the eigenvalues will become lambda 1 cube, lambda 2 cube and lambda 3 cube. And there is also 3a square, so therefore lambda 1 square, lambda 2 square and lambda 3 square, and there is also square count of minus 3. So therefore, the eigenvalues we are going to get finally lambda 1 cube minus 3 lambda 1 square, and lambda 2 cube minus 3 lambda 2 square, and lambda 3 cube minus 3 lambda cube square. So therefore, we can say lambda 3 square. So these are the eigenvalues we are going to get. So these are the eigenvalues of this overall matrix. But if you want to know what is the trace of this matrix, means just you have to do the addition of these eigenvalues, then you are going to get this expression. So therefore, we can say the eigenvalues of this matrix are nothing but lambda 1 cube minus 3 lambda 1 square, lambda 2 cube minus 3 lambda 2 square, lambda 3 cube minus 3 lambda 3 square. So these are the eigenvalues we are going to get. So now there is a coordinate transformation matrix. See, the coordinate transformation matrix is nothing but cos theta sin theta minus sin theta cos theta. And coordinate transformation matrix of mirror images. If you want to know what is the mirror image, so this is called as the coordinate transformation matrix, which is cos theta sin theta minus sin theta cos theta. And coordinate transformation matrix of mirror images. If you want to know what is the mirror image, then you have to do the, you can see, suppose if you take a mirror here, then we are going to get interchange. So we are going to get sin theta cos theta minus sin theta, and then you have to keep it theta is equal to 90 degree. You are going to get a solution. So this is the coordinate transformation matrix, cos theta, sin theta, minus sin theta and cos theta. So if you want to know what is the coordinate transformation matrix of mirror image, means just you have to put a mirror and you have to interchange these values. So sin theta will become here, also will become here. So therefore we are going to get sin theta, cos theta and cos theta minus sin theta, and we have to substitute theta is equal to 90, then we are going to get the result. See, if one of the eigenvalues of matrix A is 0, then the determinant of that matrix A is 0, because if one of the eigenvalues is 0, it indicates that the determinant of that matrix is equal to product of the eigenvalues. If one of the eigenvalues is 0, then definitely we can say that matrix determinant is nothing where it is becomes 0. And also, suppose if you want to know, if you want to do the square of sum of two matrices, which is a plus b whole square, then here you have to go for a plus b into a plus b, then a into a is a square, a into b, and then b into a plus b square we are going to get, because it is a matrix multiplication. Definitely matrix multiplication never satisfies the commutative property. So therefore we can say ab is never equal to ba. So therefore we can say finally a plus b whole square is equal to a square plus ab plus ba plus b square, because this is a matrix multiplication. Matrix multiplication will never satisfy. It will never satisfy the commutative, or we can say it is not going to satisfy the commutative property. Only the matrix multiplication will satisfy the associative property, but not the commutative property. The principal diagonal of a square matrix contains all the diagonal elements. This property I have already told you. See, if you take any square matrix, the principal diagonal is nothing but it is going to contain all the elements. We are going to call it as the diagonal elements. In a square matrix, if the data is present on the upper part of the diagonal, then it is called as the upper triangle matrix. Means the data is going to present above the diagonal, or we can say below it is 0, then we are going to call it as the upper triangle matrix. Square matrix, if the data is present on below part of the diagonal, then it is called as a lower triangle matrix. Yes, if data is going to present above the diagonal, it is called as the upper triangle. the data is going to be present below the diagonal, then we are going to count as the lower triangular matrix. See, the upper triangular matrix and the lower triangular matrix is known as the echelon matrix. See, this upper triangular matrix and the lower triangular matrix is also called as the echelon matrix. Means we are going to reduce any matrix into echelon form in order to figure out the rank of a matrix in a very easier manner. Or we can even say how many number of linearly independent row vectors are also column vectors also we can figure out with the help of this echelon form of matrix with the help of row transformation or the column transformation. Of two diagonal matrices is a diagonal matrix. I already told you the different properties has for diagonal matrix. Whether it is summation of two diagonal matrices, then the output is diagonal matrix, and the product of two diagonal matrices is also a diagonal matrix. The matrices which are obtained by using elementary transformation in the matrix A are called as the singular matrices. See, I already told you, you can do two elementary transformations. So if you do the transformations on a given matrix, then whatever the matrices you are going to get after the transformations, that matrices are called as the singular matrices. Means the rank is not going to get changed. And also here is a very important property which is A into adjoint of A. So if you do the product of two matrices which are A into adjoint of A, it is equal to the determinant of the matrix A into identity matrix. So therefore, A into adjoint of A is equal to determinant of that matrix A into I. So therefore, A into adjoint of A is equal to determinant of that matrix into I. I is called as identity matrix. So A into adjoint of A is equal to determinant of that matrix into identity matrix. And I already told you adjoint of any matrix is equal to cofactor of the matrix, then you have to do the transpose. So therefore, adjoint of any matrix is equal to cofactor of that matrix, and then you have to do the transpose. So inverse for any singular matrix won't exist. This property I have already told you, the inverse is going to exist only for a singular, or we can say non-singular matrix. Means the determinant of matrix not equal to 0. If it is equal to 0, then inverse is not going to exist. See here, if the matrix is a triangular matrix, it can be upper triangular matrix or the lower triangular matrices, then determinant of that matrix is equal to the product of the eigen of the diagonal elements. Because I have already told you, for a triangular matrix, whether it is upper triangular matrix or the lower triangular matrices, the eigenvalues itself are the diagonal elements. So the determinant of any matrix is equal to the product of the eigenvalues is nothing but is a product of the diagonal elements. Suppose there is a, if you want to figure out what is the determinant of K into matrix A, if K is a scalar number, then it is nothing but K to the power of n into determinant of matrix A, because each and every row is going to multiply by K, so therefore it is multiplied by n times, because the order of the matrix is n, so therefore you have to take it K to the power of n into the determinant of the original matrix. So where n is called as the order of the matrix A. Suppose there is a matrix A of Aij n cross n, so we can say it is a rectangular matrix because the number of rows is not equal to number of columns, and here always the rank will be, the rank of the matrix will be always less than or equal to minimum of n comma n. This point I have already told you in the rank concept. See, the rank of matrix A will be always less than or equal to minimum of the n comma n. Then if I want to know what is the number of submatrices of order r comma r, see, now number of submatrices I can figure out the number of submatrices which I am going to get from this overall matrices of order r cross r, which is nothing but MCR into NCR. So therefore, if you want to know the number of submatrices of order r cross r from this overall matrix of order n cross n, which is equal to MCR into NCR. So therefore, always the rank of matrix A, the rank of matrix A, it is always less than or equal to minimum of the m comma n. See, I have already told you the rank of A into B is always less than or equal to minimum of rank of A comma rank of B. So therefore, if you want to know what is the rank of A into A transpose, it is less than or equal to rank of A, and it is also less than or equal to rank of A transpose. But I have already told you, just by doing the transformation, the rank will be always same. So the rank of A is equal to rank of A transpose. So therefore, we can say clearly the rank of A into A transpose is nothing but the rank of A. The rank will never is going to get changed. For any matrix, if its inverse exists, then we say that matrix is invertible. See, it indicates that suppose if for a matrix, if its inverse is going to get exist, then we can say that matrix is invertible, otherwise non-invertible. For a matrix, if the inverse is going to get exist, then we say that matrix is invertible, means inverse is going to get exist. Otherwise, we are going to say this non-invertible or inverse is not going to get exist. Suppose there is a matrix A of Aij of n cross n, means we can say rectangular matrix because the order is not same, or because the number of rows is equal to number of is not equal to number of columns. The rank of any matrix will be always less than or equal to minimum of the number of rows comma number of columns. If the rank of A is equal to R, then we can say A has R linearly independent row vectors and R linearly independent column vectors. Means we can say in this matrix definitely there are R number of linearly independent row vectors and also R number of linearly independent column vectors are going to present. See now here, suppose I have already told you for linear equations Ax is equal to B. Suppose m is the number of equations and n is the number of variables. Then we are going to see the different way of relation, how we are going to get a solution or not. Suppose if the number of equations is less than number of variables. If the number of equations is less than number of variables, what we are going to get? See, if the number of equations is less than number of variables, we are going to call it as the underdetermined space. Means the number of equations are lesser than the number of variables. Definitely, there will be a no solution or the many solution. Only these two cases are going to get, but not a unique solution. See, if the number of equations are less than number of variables, we are going to call it as the underdetermined space. Means we can get either a no solution or whether we can get a many solution, but there is no chance of unique solution. If the number of equations is equal to number of variables, if number of equations is equal to number of variables, then we can get like this, whether we can get a no solution or whether we can get even a unique solution or either we can get a many solution. These three cases are going to get possible if the number of equations is equal to number of variables. If the number of equations are greater than the number of variables, then we are going to call it as the overdetermined space. Overdetermined space. Then we can get either no solution or unique solution or many solution. So you can see clearly, if the number of equations is less than number of variables, we can get either a no solution or the many solution, but there is nothing like unique solution. And in the remaining cases, we can get three conditions. Three cases are possible, which are no solution or unique solution or the many solution. So you can see clearly, if m is called as the number of equations and n is called as the number of variables. If the number of equations is less than number of variables, then only you can get either no solution or the many solution. But in the remaining cases, where m is equal to n or n greater than n, definitely you are going to get the three cases, which are the no solution, unique solution and the many solution. See here, always rank of matrix A will be always less than or equal to rank of augmented matrix. See, A slash B is also called as the augmented matrix. Always the rank of matrix A will be always less than or equal to rank of augmented matrix. Suppose the normalized eigenvector always have unit length. See, the normalization means we are going to have a length of unity. That is called as the normalized eigenvector. Suppose there is an eigenvector AB, then I want to know what is the normalized eigenvector. See, then what you have to do is, the normalized eigenvector will become A by under root over A square plus B square, B by under root over A square plus B square. Then this x is called as the eigenvector and xn is called as the normalized eigenvector. Suppose in the question they are asking, I want specifically what is the normalized eigenvector, means this is the procedure we have to do. Is A by under root over A square plus B square and B by under root over A square plus B square. If A and B are of two same order square matrices, then A into B and B into A have same eigenvalues. See, if A and B are of two same order square matrices, then A into B and B into A have same eigenvalues. See, if A and B are of same order matrix, same order square matrix, the order is same, then definitely what is going to happen is, for A into B and B into A, always the eigenvalues will be always same. Only one condition is, they should be a square matrices of same order. Then only the eigenvalues of A into B and B into A have the same values. Suppose here A into B is equal to A into C. This indicates that B is always equal to C if the determinant of the matrix A is not equal to 0. And B into A is equal to C into A. It indicates that B is equal to C if determinant of the matrix A is not equal to 0. Then only we can say this is the case is going to get possible. The equation AB is equal to 0, and 0 is called as a null matrix, does not necessarily imply that at least one of the matrices A and B must be a 0 matrix. See here, if you do the product of two matrices, we are going to get null matrix. It is not necessarily that at least one of them should be 0. See, there may be non-zero matrices, but still the product will be always equal to 0. Yes, you can get. So it is not necessarily that one of the matrices must be always 0. They both may be non-zero, but still the product you are going to get a null matrix. See, if AB is equal to 0, then it is not necessarily imply that BA is equal to 0. In fact, BA may not even exist. See, if AB is equal to 0, then it is not at all necessary. It is not at all necessary that BA is also equal to 0. Sometimes BA may not even exist because the order of the multiplication may not even satisfy. So therefore, if AB is equal to 0, it doesn't necessarily imply that BA is equal to 0. Sometimes BA may not even be exist. See, I have already told you any matrix can be written summation of symmetric matrix and also the square symmetric matrix. Whereas symmetric matrix is equal to half of A plus A transpose, whereas skew symmetric matrix is equal to half of A minus A transpose. Suppose if you want to know what is a symmetric matrix, always A into A transpose is always a symmetric matrix, and always A plus A transpose by 2 is always a symmetric matrix. So now for any matrix A, you can get either A into A transpose is always a symmetric matrix, or you can even go for half of A plus A transpose is also a symmetric matrix. See, if A and B are symmetric matrices, then A plus B and A minus B are also symmetric matrices, and AB and AB into BA may or may not be symmetric matrices. Suppose if A and B are symmetric matrices, if you do the addition or if you do the subtraction, then whatever the output you are going to get, still that matrix is also a symmetric matrix. But if A into B and B into A may not be symmetric matrices, there is nothing like necessary condition where A into B and B into A may or may not be symmetric matrices. But if you do the addition of the and subtraction of the vector of the square matrix, symmetric matrices, definitely their output is also a symmetric matrices. But if you do the product of the matrices, in either way, it may not be always a symmetric matrices. For any matrix, the matrix of A minus A transpose is always a skew symmetric matrix property. I have already told you any matrix A can be written as summation of symmetric matrix and also skew symmetric matrix. So symmetric matrix is equal to half of A plus A transpose, whereas skew symmetric matrix is equal to half of A minus A transpose. So half of A minus A transpose is also called as the skew symmetric matrix. I have already told you the transpose of identity matrix and the inverse of identity matrix, still you are going to get the identity matrix itself, and also the determinant of identity matrix is equal to 1 because all the diagonal elements are 1, and also the product of diagonal elements here, or we can say the product of eigenvalues is equal to determinant of that matrix, but the eigenvalues are itself the diagonal elements, so therefore we can say the determinant of the identity matrix is equal to 1. The inverse of a given any matrix is always unique. Suppose there is a matrix. So if you are doing the inverse, then the inverse of that matrix is always a unique. See, inverse is going to get exist only for a sphere matrix, and also their determinant should be not equal to 0. If the determinant is not equal to 0 and inverse is going to get exist, here we are going to say it is a invertible, otherwise non-invertible, and inverse of any square matrix is always a unique. And also I have already told you A into the product of A into adjoint of A is equal to determinant of that matrix into identity matrix. Or if you do in either manner, which is again you are going to get the same result, which is A into adjoint of A is equal to adjoint of A into A is equal to modulus of A into, or we can say determinant of A into identity matrix. And also if you do A transpose whole inverse, or whether you do in the reverse process, which is A inverse whole transpose, both are same. See, A transpose whole inverse is equal to A inverse into A inverse whole transpose. You can do either of the both way, till you are going to get the same result. And similarly, A inverse whole the power of theta is equal to A the power of theta whole inverse. You can do any one first, another one later, still you are going to get the same result. The rank of, suppose the rank of A into B is always less than or equal to rank of A, and also the rank of A into B is always less than or equal to rank of B. Then the rank of A into B is always less than or equal to minimum of rank of A comma rank of B. It's a very important property. See, the rank of A into B is always less than or equal to minimum of the rank of A comma rank of B. It's a very important property. And also the rank of A plus B is always less than or equal to rank of A plus rank of B. See, if you do the summation of two matrices, their net rank will be always lesser than the summation of the individual ranks. So therefore, rank of A plus B is always less than or equal to rank of A plus rank of B. And also here rank of A into B, it will be always greater than or equal to rank of A plus rank of B minus n, where n is called as the order of the matrix, and both are of the same order, which is both A and B are of n cross n. See, whether you can use this formula or whether you can use this formula, both you are going to get the same result, but it is only going to give you the range, the minimum range, and here we are going to get the maximum range, and here you are going to get the minimum range. So minimum value, what is the value we are going to get? So therefore, rank of A plus B is always less than or equal to rank of A plus rank of B, and rank of A into B is always less than or equal to rank of minimum of rank of A comma rank of B. But if you use this formula, which is rank of A into B is always greater than or equal to rank of A plus rank of B minus n, where A and B of both of same order, which is n cross n. The rank of the matrix of the given vectors is equal to the number of vectors, and the vectors are linearly independent. See, if the rank of the matrix of the given vectors is equal to the number of vectors, then the vectors are linearly independent. Suppose in the matrix we are going to have some vectors, some row vectors. If the determinant of that matrix is not equal to 0, then it indicates that all the vectors which are going to present inside, or we can say linearly independent, a rank itself indicates that the number of linearly independent vectors are linearly independent row vectors are the column vectors. If the rank of the matrix of the given vectors is lesser than the number of vectors, then the vectors are linearly dependent. Means, if suppose in the matrix there are 5 vectors, 5 row vectors, if the rank we are going to get suppose 4, it indicates that only 4 are linearly independent and remaining one is dependent on the previous ones. So therefore we can say clearly, if rank is lesser than the number of vectors, total vectors in a given matrix, it indicates that the set is a linearly dependent set. If the rank of the matrix is equal to the number of vectors in a given matrix, then we are going to say all the vectors in that set are, we are going to call it as a linearly independent. A set of vectors is said to be a basis of a subspace if the subspace is spanned by the set and the set is linearly independent. See, a set of vectors is said to be a basis of a subspace if the subspace is spanned by the set and the set is linearly independent. See, suppose any subspace is there. These vectors are said to be basis of subspace, means if you do the spanning, if you do the linear combination of any of these vectors which are going to be present in this linear independent subspace, if they are going to span all the subspace, then we are going to call that vectors are linearly independent. See, a set of vectors is said to be a basis of subspace if the subspace is spanned by the set and the set is linearly independent. Suppose there is a set, this set is going to contain some vectors, and if you do the spanning of these vectors, and if you get each and every vector in that subspace, then definitely we can say these vectors are said to be linearly independent of each other. So a set of vectors is said to be a basis of a subspace if the subspace is spanned by the set and the set is linearly independent. Suppose a set of n vectors, x1, x2 up to xn spans R to the power of n. If they are linearly independent, which can be checked by considering a matrix x1, x2, xn as its rows or columns and checking that the rank of such matrix is indeed n. If however the rank is less than n, say m, then the vectors span only a subspace of order of n. Suppose a set is going to contains of some n vectors. If these vectors are going to span, or if they are going to span R to the power of n, means we can say these n are linearly independent vectors. Or if we can check the, suppose by taking the matrix with this column vectors, whether you can go for row or column, and if you get the rank is equal to indeed n, then we can say all these vectors are linearly independent and they can span a space of R to the power of n. Suppose if some of them are going to be dependent, then we can say the rank is less than n. It indicates, suppose we are going to say this m, if m is less than n, then definitely we can say this is not going to span R to the power of n, but it is going to span only a subspace, only a part of R to the power of n, but not fully. So therefore we can say clearly, if all these vectors are independent, then only they can span R to the power of n. Otherwise they are going to span only a subspace, means a part of R to the power of n. N vectors x1, x2, x3, xn, each of which is in R to the power of n, are orthogonal, then they are surely linearly independent and hence span R to the power of n and therefore form a basis for R to the power of n. Suppose, see here, suppose there are n vectors. If these n vectors are orthogonal vectors, means orthogonal vectors itself indicates that these are linearly independent. So linearly independent means they are going to span the overall of R to the power of n space. So therefore we can say even call it as these orthogonal vectors is also called as the basis for this subspace, or we can say these are linearly independent. Suppose there is a q of x is equal to x transpose into a into x, where x is called as the eigenvector and a is called as just the matrix for this one. So x is the eigenvector of the matrix A. Then homogeneous polynomial of second degree in many variables. So this is called as the homogeneous polynomial of second degree in many variables. So where q of x comma x1 comma x2 comma x3 is equal to, here X is nothing but x1, x2, x3. So X transpose will become now, because it's a column matrix. So you are going to get the row matrix x1, x2, x3. Here it is a 3 by 3 matrix, because it is a 3 by 3 matrix. We are going to get, so a11, a12, a13, a21, a22, a23, and a31, a32, a33. So if you do the multiplication of this matrix, finally you are going to get, this is the way you are going to get as a matrix. So this is called as a homogeneous polynomial. This is called as a homogeneous polynomial of second degree. Yes, so degree is 2, also degree is 2, also degree is 2, also degree is 2. So here also degree is 2, and here also degree is 2. So therefore we can say homogeneous polynomial of second degree in many variables. The variables are x1, x2, x3. Suppose if you are going to take in terms of 3 variables, then you are going to go x transpose into a into x. So this is x1, x2, x3, and is the matrix of 3 by 3, and is the also x column vector. So with the multiplication, finally you are going to get, in this manner you are going to get some equation you are going to get, which is a11 x1 square plus a22 x2 square plus a33 x3 square plus a12 plus a21 x1 x2 plus a23 plus a32 x2 x3 plus a31 plus a13 x3 x1 you are going to get. So this is the equation you are going to get finally. If a matrix A is of size n cross n, and if it has n distinct eigenvalues, then there will be n linearly independent eigenvectors. However, if the n eigenvalues are not distinct, then there may or may not be n linearly independent eigenvectors. Suppose if a matrix A is of size n cross n, and if it has n distinct eigenvalues, then there will be n linearly independent eigenvectors. However, if n eigenvalues are not distinct, then there may or may not be n linearly independent eigenvectors. See, listen, suppose if there is a matrix of A of order n cross n, suppose if the eigenvalues which you are going to get, if there are n distinct eigenvalues, then definitely you are going to get n linearly independent eigenvectors. But if suppose you are going to get lesser than n eigenvalues, means distant, means some of them may be equal, then at this condition you may get n different n or lesser than n eigenvectors you are going to get. See, now if suppose some of them are equal, then you may or may not get n linearly independent eigenvectors, means you can get n linearly independent eigenvectors, or you may get even lesser than n linearly independent eigenvectors you can get. See, this property I have already told you in the diagonalization, which is D is equal to which is P inverse AP, or you can go for PA P inverse. You can do it in any other mode. And if you want P, then you can go which is PD P inverse, or you can go in another fashion which is P inverse D P. But a to the power of, or you can say I have already told you, D to the power of n is equal to P inverse a to the power of n P, or you can go for P into a to the power of n P to the power of minus 1, or P inverse. But if you want a to the power of n, then you can go for P into D to the power of n into P inverse, or you can go in another fashion which is P inverse D to the power of n into P. So simple, D is equal to P inverse AP. You can do it another way also, which is P into A P inverse. If you want D to the power of n, just you have to go only for the A to the power of n. Remaining everything is same as the previous one. And also here if you want A, which is P into dp inverse, or you can go to another fashion which is p inverse into dp. If you want a to the power of n, just you have to go for the d to the power of n. Determinant is defined only for square matrix. Yes, this property I have already told you in the determinant concept. So determinant is only defined for only square matrix but not for the rectangular matrices. If all the principal minors of matrix A are positive, then all the eigenvalues are also positive. This property also I have told you. If all the principal minors of the matrix A are always positive, it indicates that all the eigenvalues of the matrix A are also positive. Suppose if there is a matrix A of A, B, C, D, and when A greater than 0, then for all eigenvalues of matrix A are greater than 0 when determinant of A greater than 0. So it is a very important property. If A is equal to A, B, C, D, and when A is greater than 0, then for all eigenvalues of matrix A are greater than 0 when determinant of A is greater than 0. Suppose it's a 2 by 2 matrix. Here they are going to say that if A is greater than 0, then definitely all the eigenvalues are also positive whenever the determinant of that matrix is always greater than 0. This is an important property. Suppose there is a square matrix of A, J, n cross n, then always the squares of sum of eigenvalues is always lesser than or equal to square of each and every element present in the matrix A. So therefore it's a very important property. Always the sum of, or you can say the squares of eigenvalues sum is always less than or equal to the squares of sum of each and every element present in the matrix A. So therefore we can say lambda, suppose it's a 2 by 2 matrix, then simply we can say lambda 1 square plus lambda 2 square less than or equal to a11 square plus a12 square plus a21 square plus a22 square. So this is a very important property, which is squares of sum of, or we can say sum of squares of eigenvalues is always less than or equal to sum of squares of each and every element present in the matrix A. Suppose there is a 3 by 3 matrix of this fashion. Suppose A is equal to ABC, CAB and BCA. So you can see clearly, if in order to find out one real eigenvalue of A, then always determinant of A minus lambda I is equal to 0. In this case, take summation of any one row and equate to 0 and then find out that one real eigenvalue. So there is a special matrix. So you can see clearly ABC, here A, B, C, I get A, B, C. Suppose in order to find out one real eigenvalue of A, then what you have to do is, for the special matrix, if you want to find what is the one real eigenvalue of A, then what you have to do is, first you have to take a matrix of A minus lambda A and then the determinant is equal to 0. So for this matrix A minus lambda I, for this matrix any one row, take any one row and do the addition of each and every element present in that row, and if you do the equal to 0, then definitely you are going to get some lambda. That is called as the real eigenvalue. So in this, take summation of any one row and equal to 0 and find out that one real eigenvalue. So for this special matrix, the easy way to figure out the eigenvalue, one real eigenvalue, is first take a matrix of A minus lambda is equal to 0. In this matrix, you can take any one row and do the summation of that row is equal to 0, and definitely you are going to get that one real eigenvalue. To be basis for subspace X, two conditions are to be satisfied. The vectors have to be linearly independent and they must span X. See, here suppose there is a subspace. See, the vectors which are going to be basis of subspace X, they need to satisfy two conditions, which is the vectors have to be linearly independent and also they must span the overall space of X. Then only we can say these two vectors are said to be a basis of the subspace. The value of the dot product of the eigenvectors corresponding to any pair of different eigenvalues of n by n symmetric positive different matrices is always 0, because I have already told you, for a symmetric matrix the eigenvalues are, you can say, they are always real. They may be positive, they may be negative, they may be distinct, or they may be same. So we can say the value of the dot product of the eigenvectors corresponding to any pair of different eigenvalues of n by n symmetric positive definite matrix is 0. Means here, suppose if the eigenvalues are different, then definitely with the help of eigenvalues you are going to get eigenvectors, and these vectors, eigenvectors, are always orthogonal to each other. That means if you do the dot product, then definitely you are going to get the result as 0. See, there is one important property. See, linear independent vectors, it is not necessarily they have to be always orthogonal, but every orthogonal matrices, or we can see every orthogonal vectors, are definitely said to be a linearly independent. So you can see clearly, if linearly independent doesn't guarantee orthogonal, but orthogonal guarantees they are the linearly independent. So here is a very important property. So now for every n by n matrix with only real eigenvalues, if the trace of the matrix is positive and the determinant of that matrix is negative, then at least one of its eigenvalues is negative. So it's a very important property. Suppose for every n by n matrix, means a matrix of n by n order with only real eigenvalues, means it is going to have only real eigenvalues. If the trace of the matrix is positive, see, the trace is nothing but you have to do the summation of the eigenvalues, and the determinant of the matrix is negative, means we can say clearly determinant is called as a, we can say simply it's a product of the eigenvalues. If it is a negative, it indicates that at least one of the eigenvalues should be always negative. This is also one more important property of eigenvalues, which is Ax is equal to lambda x, where x is called as the eigenvector of matrix A and lambda is called as the eigenvalue for that eigenvector x. But if you go for the another one, which is a to the power of n x, a to the power of n x is equal to lambda to the power of n x. So you can see clearly the eigenvector is still the same, but only thing is the eigenvalue is changed by lambda to the power of n for a matrix of a to the power of n. So if you do the matrix of a to the power of n, the eigenvalue will change by lambda to the power of n, but still the eigenvector will remain same as it is. So therefore we can say clearly, if Ax is equal to lambda x, then a to the power of n x is equal to lambda to the power of n x, means if you do the a to the power of n, the lambda value will increase by lambda to the power of n, and also the eigenvector is still the same. Some of the important formulas of the linear algebra. So if you understand all these concepts with just a quick revision of the mathematics subject of important formulas. So if you understand all these formulas, then definitely you can solve any question in the linear algebra which are going to be useful for the IAS exam and also the GATE exam, and also some of the state examinations also they are going to use this mathematics portion for competitive examinations. So I hope you have all understood these concepts. So if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever we upload new video, a direct notice comes to your mobile. If any improvements today in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. Thank you so much for watching this lecture. Keep smiling and take care. Bye bye.